enumeration. Time sharing option, that's the shell. So this is the shell that you run. Oh, that's perfect, thank you. Is that better for folks? Yeah, much better, okay. So, time sharing option. Anybody know why it's called option? No? I'm not gonna ask, like, it's optional. It was like, remember the terminal? That terminal was the master console. So time sharing was optional and was not included in the operating system. And you paid for it as an optional product add-on because you had terminals that people would use. Now it's just included as part of the operating system. But things, you know, legacy doesn't change the name. So time sharing option, it's that red ready prompt. It is the interactive way that you interact with the mainframe. This is where I spend most of my time during pen tests when I'm doing stuff, unless I'm doing, like even submitting jobs through TSO and stuff. You can use it to run scripts. So like here you can see a little cactus I made up for a Rex script. Rex is great. You can call, you don't execute programs, you call compiled programs. It took me, when I first started doing this, it took me 2 hours to figure that out. Okay, yes, Dave? Do you have the nice command in time sharing? No, there's no nice anything about this operating system. It's by engineers for engineers. Hope you like reading. So you access files with ISPF, you submit jobs, you profile, so there's a whole bunch of stuff you do in TSO. Rex is the best. Rex is a scripting language, very popular in well-known operating systems like ZOS, ZVM, OS2, and Amiga, right? That's who uses Rex. It's a very niche community. But it lets you do a whole bunch of stuff. It lets you create sockets. It lets you profile. In fact, a lot of my tools, we will rapid prototype something in Rex to see if it's feasible, and then rewrite it in assembly because it's slow as hell, right? Because it's an interpreted language. But it's very powerful. The thing that it doesn't have is arrays or dictionaries or anything like modern, right? But it's good enough. So, like I said, we rapid prototype in Rex, then we write the actual tool in assembly. I hate assembly, but what's that? I get why. Yeah, it sucks. The other thing I don't like about it is like whenever I write assembly, I feel like I'm finally looking through the looking glass, and then you realize like everything's just a giant calculator, right? Because you have to hand write your for loops, you have to hand write everything. It super sucks. And also you have to manage your memory, and yes, go ahead. Yes. So the question was, is there any memory segmentation? Yes, each user gets their own virtual memory stack. There are ways, if you can get APF authorized, to see other people's memory, and there's a tool being worked on I can't talk about that may or may not let you see things that other people are doing. But yes, so like as a regular user, you are isolated to your, and regular processes not running authorized, you are isolated to your sort of own virtual memory stack. So I write my tools in assembly. They're very fast. So for example, I have a tool called CatMap I'll talk about later. In Rex, it took hours to run, and in assembly, it takes 10 minutes. Right? So huge difference and huge speed up in time. But it's the opposite. To write it in Rex took me 10 minutes. To write in assembly took me 3 weeks. So little bit of a time spent there, but huge savings on pen tests. RACF, so yes, question? You'll see later when I'm talking about the tools, you'll see why. Because there's specific like calls and macros I'm using that are not available in the other programming languages. Yes, another question in the back. Oh, okay, I love this interactivity, by the way. Don't worry about it. I will cram through slides quickly in the end if more people have questions. Okay, so RACF is the security product. There are 3 security products, which is the other reason why we use assembly. There's RACF, there's Top Secret, and ACF2. RACF is by far the market leader with like 80 to 90% of the market. The way it works is the operating system goes to what's called a SAF router in the OS and says, hey, is my user allowed to access this file or this resource? And then the router is set up, configured to talk to one of those 3, whatever one you installed, and then it responds back and says yes or no. And it's all stored in a database but it's not really a database because you can't access it in any meaningful way. It's just called the RACF database. You have to use TSO commands to do any kind of work with the RACF database, right? It's not like a SQL database or anything like that you would be used to. It was written, again, it was written in the 70s. So the file system is flat. There are no directories, there's no hierarchy, there is nothing, right? It is a flat file system. Max file name length is 44 characters, but it has to be broken up into 8 alphanumeric chunks followed by a period until you hit 44 characters, right? So that's why you end up getting like very weird spelling of like, you'll see, vowels just disappear because you don't have the space, right? Folders. So folders, I'm gonna call them folders. People call them libraries. Really what it is it's a flat file that the header of the flat file has pointers and it just divides up the flat file into chunks. So it's still a flat file, but it's been sort of like logically divided up so you can store files in it like a folder, okay? And they do that because you get it, there's reasons. Yes, question? I have no idea, I don't touch AS400s. That's not a joke, I don't, like, This looks similar, they call stuff libraries. Yes. Yeah, because AS400 was like, oh, people can't afford this big one. What if we made a smaller one with a different operating system and the skills don't translate? It's very classic IBM. So, it also runs Unix. AS400s also run Unix. So, z/OS runs Unix. It drives the networking stack, but it also comes with everything you expect a POSIX compliant Unix to have. I'm being very careful. Unix. It's not Linux. Doesn't come with a bunch of the commands you expect it to. grep doesn't work the way you expect it to, but it's there. I use it to write code and stuff. Look, it's just Unix. It's just regular Unix. Like I'm not gonna let that whole GIF play. APF authorized, right? So think of a setuid program in Linux, right? Or Unix, right? You assign it, or a directory, you assign it, setuid so that when the program runs, it can run as whatever UID it's set to. Now imagine instead of that, it was a folder, and anything in that folder inherited those permissions. And then imagine if it, instead of being setuid, it was kernel. So anything you put in these folders runs as the same authorization as the kernel does, essentially ring 0, right? So yes, question? Yes. It's why I'm here today. So this is what we target in every single freaking pen test. We are trying to get APF authorized. If we can, it is game over and I can do anything I want on the system because I am in what's called on the mainframe key 0. Key 0 lets me edit anything in memory, and then from there you can kind of just do whatever you want, right? And there's reasons why we'll get into in a bit. Okay, let's talk about how we actually do the pen test. Also, I want to point out, I put a typo. There's no space between hand drawn. That's why I think it added a hand for some reason to this picture. So good old AI art. All right. When we do, so we typically start with a network pen test. Network pen tests are just network pen tests. It's not super special, right? You need an IP address, and that's all I need to start going after the system, right? Think of all the tools that you would use in a traditional network pen test or web app pen test. It's the same. It's just a computer, right? Yes, the architecture is different. Yes, the file system is different. But at the network level, it's literally just a computer, no different than any, except for when we talk about SNA in a second. But, okay, so myth number 1 that I have to dispel all the time. Will port scanning a mainframe cause it to crash? Show of hands for yes. I called it a myth, guys, come on. Show of hands for no, right? Yeah, no, if it was, it's the year 2024. If Nmap was crashing like Bank of America's mainframes, that would be a major frickin' problem, right? Like you can't, oh sorry, ATMs are down because some like compliance dude ran Nmap, right? Like, come on. All right, so no, port scans haven't brought down a mainframe since the 90s. It's a big old myth. If you want, if we have time, I can tell you why that happened later, or just come find me after and explain why they crashed mainframes in the past. I just use Nmap, right? Why do I use Nmap? because I'm the one that wrote all the tooling for Nmap. I would say 10 years ago, 15 years ago, Nmap had no idea what to do with the mainframe. It would tell you the wrong operating system version. It'd be like, oh, this port is Telnet, and that's it, right? I rewrote the probe files to include a bunch of mainframe stuff, and because I don't like myself very much, I wrote a Lua TN3270 emulator for Nmap, okay? And the whole library, and then on top of that, a whole bunch of scripts to use that library. And if that interests you, I'm teaching a workshop tomorrow about Nmap scripting and how to write scripts and profiles, and it's not mainframe based at all. So if you're like, fuck this, that's fine. Come to the workshop tomorrow, there's no mainframes. Okay, so now this is what, when you Nmap a mainframe, this is what it looks like today. This is literally yesterday, I was working on my slides yesterday. So this is what it looks like now, okay? I'm gonna walk you through all of these as we go through. So first things first, we're gonna look at this. This is TN3270, or as I like to call it, the gateway to the mainframe, right? Because really, when you connect to TN3270, you're connecting to a different type of network, right? So now you're going from TCP/IP to SNA, and there's like week-long trainings about SNA, so I'm not gonna get into specifics, but essentially, now that I'm in here, it's like a text adventure game, and I'm trying to figure out what applications you're running by trying to connect to them. So how do we scan SNA networks, you might be wondering? Well, you do it by hand, right? So this is my mainframe, and for those in the back, down here, I'm typing, that's supposed to happen. You type log on, then the application ID you want to connect to, and then you guess a name. And if it takes you somewhere, you found an application. If it disconnected you, then you didn't, right? Now, obviously those are two like simple examples, but that sucks doing by hand. So instead we just use Nmap. Nmap A has a brute force library, so I don't have to do any threading myself, because I hate it. The other thing is I can use all the facility, and the other thing I like using Nmap is it comes to you. You all, if you're running Kali, you can do this right now, right? You don't have to go to my GitHub. It's readily available for you right now. So here you can see I'm running the VTAM. VTAM is what runs the SNA server. I'm using VTAM enum, and you can see we found a valid application ID TSO here. This is a dumb example. Typically, you'll find dozens, right? And you'll find multiple different setups. So you might find Kix regions, and there's like a whole bunch. Some of them labeled prod, some labeled dev, right? And you can find things like the dev one might not be as locked down as the prod one, but they're all running on a production mainframe. From here, we would typically just I can enumerate all the users using TSO, especially through SNA. There's a setting to not allow you to enumerate users, but very rarely have people turned it on. So I have a script that will let you enumerate the entire user space, and then you know all the users that can use TSO. And then from there, we typically just do like a password spray, like one password, like month at year will get you in if there's enough users, right? So like Walmart, or like a company with a large call center will have thousands of people using their mainframe. They all need mainframe IDs, and a bunch of them will pick bad passwords. Okay, so that's TN3270. Let's talk about like a regular ass web server, right? This is just a regular web server running Apache, right? I literally installed this on Monday, right? So it's just the most recent version of Apache. So this actually happened on an engagement where I found this web server, and I was like, okay, cool. What do you do when you find a web server? You run nicto, right? And then it found default creds set up. Why? Like, you have to go out of your way to set up default creds, but I guess they did. And then from there, I was in the system, and I was able to like run shell commands. And you just use Metasploit, legit just use Metasploit or MSF Venom to create the WAR file, and then you have a reverse shell through Tomcat on a mainframe. Like, it's not, that's the thing, like, yeah, it's foreign, but at the network layer, these kind of attacks just work, right? So, and mainframe for a long time was excluded from pen tests because people were like, oh, you can't touch it because you'll bring it down. But also people were like, well, we don't want someone who doesn't know what they're doing touching it. Everyone here should be able to hack a web app, right? Like, it's not that different, except for this. So this one is different. This is called Shadow Web, And for people who I used to work for might recognize it. But I'm being vague and not specific. So what's nice about Shadow Web is it comes with, by default, it's a Rex web server, and by default, it comes with the ability to browse the source files for your web server. Cool. The way it does that is through this. This is like abbreviated and is not the exact one, but something similar to this, where this looks, to me, for me, this looks very familiar. Couple of characters and then a dot and then and it's an uppercase. That looks like a data set to me. That looks like a member within that data set. So what am I going to do with that? Well, first I'm going to try, well, I know what exists on every mainframe. There is a thing called sys1.samplib. That's the, like, they put all the samples of things you would do. That always exists on every mainframe, right? So I just downloaded that file. And then from there, I was like, well, maybe I can download the RACF database. And then once I download it, you can crack the RACF database with John the Ripper. And then you just have and especially if they're only using 8 characters and they haven't enabled AES encryption on the passwords, you can crack every single user with an AWS cracking rig within a day. By the end of the day, you have every single user, right? I didn't do that because I found a bunch of admin users like on my MacBook, and then I didn't bother cracking the rest. Okay, so that's the web server. Oh, that was web servers, right? And I don't run Shadow Web on my lab because you have to pay for it, and I'm cheap. Last one, a sticker to whoever knows what this port does. It's not VMnet. I'm going to walk, because you answer some questions, I'll give you a sticker already. I'm going to take a little walk, take a break. Anyone want to guess? You can't even look it up. It's so esoteric. No one's going to get this. Anyone want to yell? There's no wrong answers. Someone yell out an answer. I already mentioned it once. It's not Telnet. Really? Has anyone been? No, it has nothing to do with web. I already mentioned it when I was talking about jobs. So there are a bunch of wrong answers, it turns out. What if I say the first word is network? The second word is job. It's, okay. It's network job entry, all right? This is the port. In fact, this is something we literally discovered this week. Yeah, you were close, Dave, I'll give you a sticker. We discovered this week in the mainframe hacker community. You used to be able to send a probe, like a very specific packet, it's in the mmap profile if you want to look at it, and then it would come back and tell you, no, that's bad, and now it just resets the socket. So IBM has prevented us from even probing the port. But I know what the defaults are, and no one changes the defaults, so who cares? It's 175 and 2252, that's network job entry, right? Network job entry, it is amazing. I've written an entire Python library about it. So network job entry works like this. I'm in a mainframe in Orlando, and I need to talk to a mainframe in Phoenix. All of my JCL is on the mainframe in Orlando, but the data I need lives on a different mainframe. So in the job card, I say, don't run my job here, run my job on that other mainframe. You don't need to pass a username or password. You don't need to provide credentials because the nodes are trusted. So one node is trusted. So in part of the packet, there's a header in the packet that is the username of the user that submitted it. And if that username exists on the target node, it runs as that user. And what we find is over time, companies consolidate. As the mainframes become more powerful, they consolidate down from 5 to 3. But they don't delete those trusted nodes in the settings. So then we connect with this Python script and pretend to be one of those trusted nodes, and now I can run as any user, even if that user is locked. Okay? That's network job entry. It's amazing. So how do we test it, though? Like, how do we like find the nodes and all that stuff? You're never going to guess it. We use Nmap, right? We run an Nmap script, and this is how we find. So these are called our host and the O host. These would be the things you're trying to figure out, because this would be the system you're attacking. I don't have the time, because I got like 23 minutes left, to get into the details, but if you really want to get a deep dive on network job entry, I gave a talk at Wild West Hackin' Fest that's literally in the bits and bytes of network job entry. Like, it gets down really deep, very technical. I also have an article in POC or GTFO that goes into detail about the protocol as well. So if you really want to learn about network job entry, you can go read those. Okay, so we're in now, right? Like, eventually we get in, right? It's just a matter of time, right? Sometimes on red team engagements, we just say, what was their Windows password? And then that works, right? Like, eventually we get in. It's not hard to break into mainframes. But once we're in, that doesn't mean we necessarily can do anything, right? So what do we do next? Who here has their OSCP? A person. Great, I'm so glad I have that cert. Really great. OSCP, the rule is you enumerate, right? Like, you have to gather information. So we have a whole bunch of things to enumerate the system. Someone asked earlier, why do we write in assembly? Like, why not use C or Java? I'll talk about Java later. Because we use things like the very clearly named IGGCSI00 and rack route. So IGCCSI, that's the catalog interface. And then rack route is how we check access. In fact, this is, over here, this is the rack route call. So all we're doing is saying, show me all the files that exist on the file system, and show me my user's access rights to those files. That's what's happening. So here, for example, this is what the output looks like, right? From here, what I'm looking for are things like data sets named JCL-lib, data sets with the word rackf in them, data sets with the word HTTP or FTP. Since it's batch-driven, people use JCL to FTP files around. They put their creds in the JCL. So if I can read those files, this has happened. You can get their username and password, and they didn't even know those files were world readable, right? Because it's not as easy to tell like it is in Unix. If you look at this carefully, you can see my janky shell script that I use in Unix because I tried to compile TrufflePig using Rust. There's a Rust compiler for ZOS. The compiler crashed while I was trying to compile TrufflePig. So we use this janky. It's one of the tools I'm working on now. I'm working on a Java tool to do this instead that will consume TrufflePig. Anyone knows what TrufflePig does? TrufflePig, you get a bunch of YAML files with regex, and then you check files that you have access to if that regex exists, and it finds passwords and keys and all kinds of stuff, right? I want it to run on the mainframe, but that's not going to happen. So I have to write it myself. So because I have access to data sets, I check what I have access to, right? The other thing we have is a Rex script. And this one is written in Rex because it was easier, but also because it doesn't need to be assembly. This is a Rex script that enumerates a whole bunch of things in the operating system. Remember that first picture where like hard disks and stuff? Hard disks are expensive from like a cost perspective, but they're also expensive from an I/O perspective. And the mainframe is all about speed. So it puts everything in memory. And this script reads everything from memory because it's all there. Some of it documented, some of it not. So for example, look, if I'm all imposter syndrome-y on an engagement on my first day and I'm like, why am I doing this? And I'm gonna get fired. I will run this script with the sec argument and I will get this and I will instantly have my first finding because it will say there's no password rules defined or the password rules suck and I can go and say, hey, your password rules are bad, right? That's easy wins for me and then my confidence starts to go up. And then by the end of the second day, I've got APF authorized, and I've owned the system, right? But is it easy? Like, every mainframe I've been on, the password settings have been like, yeah, I guess it can be like 5 to 8 characters, but you don't have to have any special characters. And we don't save the history, right? Typically, to get this information, by the way, you would need to have admin rights to but it's all in memory. It's just not documented. Yes? Yes, but it's called walking the control blocks. You'll see another example of that when I talk about the privesc. Okay, so that's all the TSO side of enumeration, right? What about, and we're going to talk about APF enumeration later. What about Unix? Has anyone used linps? Right? Yeah, I tried to run it. Someone told me like, oh no, it totally works on Unix too. It doesn't have to be run on Linux, and it does. Let me tell you, it did not. I ran this on my mainframe, and it was like, no, no, and like all the graphics were all messed up, and it just didn't work. If anyone wants to talk to me later about, rewriting linps and pushing that up to their repo so that it supports mainframes, let me know. But if you're like a shell programmer, but I wrote my own called OMVS enum. It's like linenum. It's in fact almost copy and paste based on linenum, and then I added a whole bunch of mainframey things to it. The shells that come with Unix are binsh and tcsh. That's the two shells you get. You can install bash, which I have on my environment, but that's the two environments you get. And they are, like you can't even, on binsh, you can't even press the up arrow, and like if you typo something, you can't press the left arrow. You just have to like Control C and retype it. Yeah, it's super painful. So again, this script maps out your access. I've used this successfully. I found on an engagement a script that had credentials in it because it was doing like a call to another web server to do something in an API, and it had creds in it, and I used those creds, and that application had access to APF authorized libraries, and then I owned the mainframe, right? And I found it only because, and that system was so locked down, I was so stressed out by day 3, and then I found this file, and I was like, oh, thank God, right? So, always look in Unix. I call it the gateway drug to mainframe hacking because everyone knows how to use Linux, right? So, we check for other things too. So, like all the files, everything's mounted, and those are data sets that are mounted. And if you have write access to those data sets, you can change the bit of at the bit level for the file system and maybe make it set UID 0. Or maybe make it APF authorized by editing the actual bits in the files that are mounted, right? So there's all kinds of fun tricks we can do on the mainframe in the Unix side. This is what it looks like when you run this script. It goes for pages and pages. Like there's not enough space here. It would be like down to the door if we let it run. But it tells you all kinds of information about the system. In fact, I have an engagement coming up that's just Unix. Someone's like, nah, we don't want to look at the rest of the operating system, just Unix. I'm like, but I can't not look at the rest of the operating system. Anyways, so yes, so Unix is fun. You could probably do a whole engagement. Okay, next myth. There's only 2 myths. I started this presentation like, I'm gonna have so many myths. There's really just 2 big myths. Buffer overflows aren't possible on the mainframe, right? Who here has heard that? Or believe, yeah, thank you. It was true, not because you couldn't do them, but because no one had come along with the ability to do them, right? In 2020, this myth was shattered by Jake LaBelle. Jake LaBelle is a cybersecurity researcher based out of the UK. He gave an amazing talk on buffer overflows at DEF CON on ZOS. I strongly recommend you go watch it. It turns out there were a bunch of APF authorized programs that had overflowable arguments from the command line. So you just type a command and then overflow the buffer, and now you're APF authorized, right? And this had been around for decades. And we had been told, in the mainframe community, you were told, buffer overflows are impossible. That's why this operating system is safer. And it turns out, no. Yes? The idea was that so there's no stack on the mainframe. The registers are different. There's no return pointer. So people thought like, well, because we don't have those things, but you still, when you write a program, it still has to know how to go back to where it came from. So you still have to have some kind of return pointer. You're just responsible for storing it. And it turns out there's something called the language environment, and everyone uses register 13 to store the return pointer. And if you can overwrite register 13, which you can in certain cases, then you can control where you're going to go on the stack, and then it just becomes about finding where you need to go, right? And if that was interesting, that was a great segue, thank you. If that's interesting to you, we taught a workshop at DEF CON about mainframe buffer overflows. We start with a very simple C program. We move to an assembly program that's overflowable. Then we move to a remote code execution. We teach you how to write shell code. This is a self-paced Docker container. It runs the mainframe in your container. The course is all at a wiki. If you want to learn about JCL and writing mainframe buffer overflows, please, it's all freely available. You can run it. And if you get stuck, which you will, feel free to reach out to me. I will gladly help anyone who is interested in doing this, because we definitely need more researchers in this space. So that's buffer overflows. I'm not going to talk about specifics, specific ones, because that's too dangerous, but it is possible, and we do check for it. Like, I check for all the ones I know about. That's the first thing I check when I get on the box. It's like, do these exist? Oh, no, they're patched. Okay. Right? Okay, so last one is access to APF authorized programs. APF authorized, like, again, we said, if I can get here, I can get to key 0. So we have an assembly script. We have an assembly program that will check your access rights. It uses rack route. The reason we use assembly, again, is because rack route is what we call ESM agnostic. So it checks rackf, ACF2, or top secret with one command instead of me having to program them all and figure out what we're doing. And it's also fast as hell, right? So here's an example. And you can't prevent people from running a rack route macro. You can prevent people from running rackf commands, but you can't stop someone from checking their permissions with assembly. So here I'm looking for things like, so update or alter. Right? So those are the two. If I see that on a pen test, I get very excited. And then I run downstairs because I work from home, and I tell my wife about it. And she's like, cool, can you pick the kids up from school today? And I say, I guess. And then I go back upstairs, and then I text like a friend, and they're way more enthused. Right? So from here, we do this. So a sticker, again, to someone who can tell me what this does. I'll tell you what, I'll give a sticker to except for you, you've already guessed. I'll give a sticker to a person who just guesses. I'm going to give you a sticker anyways because you've been very participatory, so don't worry about it. I mean, you can guess. That's absolutely what it's doing. Holy shit. So, come on up, get a sticker. Come on. So here's what's happening here. Here's what's happening. Remember I talked about walking the control blocks earlier? In memory, so like I said, there you go. Oh, thank you. So for those who didn't hear, you said I really like this presentation. Making it clear. So in memory is your access rights. Why? Because imagine it's the 70s, and every call center person is logging in at the same time. And all of a sudden, they're checking access to files, and that's all happening at like 9 a.m. If it had to go to disk every time it did that, the system would slow down to a crawl, like tapes and stuff, right? Disks were very slow. So instead, your access rights, for the most part, like the important ones at least, are in memory. In rackf, the concept of special and operations, special is root, special and operations is essentially root on a mainframe. That is controlled by 2 bits in memory, not bytes, bits. And if we can change those bits, then we can become super users. Only problem is that region of memory is in key 0, which means we as users are usually in key 8. We cannot change it. Unless we're APF authorized, that's what this mode key 0 does, is it changes us into key 0, and this literally finds that bit and changes those bits. And how we use that is typically we will put it in this JCL as an inline program, but there's no room on the slide. There's 3 steps to this job. The first step is we assemble and link the exploit, the privesc. Then we run it. And then because now we're super users and it's ephemeral, right? Because it's only in our current session's memory, we then run this command, which makes it permanent. This is altering the user, give them system special in the database itself. After this, I log off, log back in, now I am root on the box, okay? You could run this from the TSO command line, but again, it's ephemeral. So here's what I'm doing, right? essentially what's happening in memory is this, right? Changing those bits in assembly, but then you have to do it to keep it. Yes? So the question was, is this something that blue teams would get alerted to? It absolutely is today. Well, okay, blue teams maybe not. That's a whole other can of worms. But like mainframes are, like socks on the mainframe, about 10 years behind the rest of everything else. So nowadays, if you do this, there's an alert that will show up on the master console that says, this person is not special in the database, but somehow they're special. That's a problem. You need to look into it. Does anybody follow up on those errors? Not in my experience. Okay? Like I've been on pen tests where I've done just exactly this, and they're like, how'd you get system special? I'm like, well, I had access to API authors. Like, how come we didn't find out? Like, there was an alert on your console. I saw it because I was the admin. Yes?
Is there any way to get that alert like out of the socket?
Yes, there is a bunch of tools. I can talk after because I got 7 minutes left and I still got to go through data exfiltration. But again, this tool is like, look, I don't expect you to remember how to write all this assembly and shit. There's a rec script that'll do it for you, written by a hacker named Ayub. You can just go download it and run it. Please don't hack mainframes unless you have permission, though, because you will get in a metric ton of shit if you do, just from experience. So, data exfiltration, right? This one's my favorite. This one, expitication is what the AI says. Data exfiltration is stupid easy on the mainframe because it has a whole bunch of tools for moving things off the mainframe. You can use FTP, SCP, but there is a problem using all these things. Does anybody know why there's a problem moving things off the mainframe? Dave?
SNA to TCP/IP translation?
That, no. It's way wrong. Yes? No, it has nothing to do with that. It's because the mainframe is EBCDIC, not ASCII. So, everything does it differently. Every single one is like, sometimes it's binary, sometimes it translates. It's up to you to figure it out. So here's a handy chart. FTP, you can do both. SFTP only does binary. SCP only does translation, right? There's like, you just have to know these things. How do we, so this is a fun one. I am pushing for people, and I'm gonna make this offer here. If you know like how to write Java or C, you could write a C2 proxy for the mainframe, because in my experience, mainframes typically have a port or 5 that are allowed to talk just to the internet straight without going through any proxies. Why? Because that's how someone set it up 30 years ago, and no one wants to change it because they don't know what it does, right? So how do we find those ports? On AWS, I run Egress Buster. Does anyone use Egress Buster? It's super cool. It opens up every port. And then the other problem is Egress Buster comes with a Python script to run on the local host, except we don't have Python on the mainframe. Like it exists. I run Python on my mainframe, but it's not really installed anywhere. So we have to write our own port checker. Well, the problem is we can't do it in Rex, we can't do it in C, and we can't do it in assembly because the timeout, that we can control the timeout, the smallest we can get is seconds. 1 second times 65,000 is a lot of hours, right? And that's gonna take forever to check every port. But thankfully, a gentleman by the name of Sir Kix-a-Lot, who couldn't be here, goes by Owen, he figured out that in Java, we can use the old legacy style sockets that allows you to declare it in milliseconds, and then we basically do a SYN flood from there, and we can check every single port in seconds. This is what it looks like. You run the tool in Java, and then after that, you look in your console in your cloud, and you get a whole bunch of ports that are open, and again, I get easy findings in my report. But here's the key. We were talking about log and monitoring earlier. If you can do this, and you have an account on the mainframe, you can probably run a C2 proxy through the mainframe and no one's gonna look at it, right? Oh, this workstation's talking to the mainframe, cool. This mainframe's talking to some host in the cloud, I guess that's okay, we don't know. Because the SOC doesn't know, they call up someone on the mainframe side, they go, we don't know, we're not the firewall team, call the firewall team, right? So it's untapped goldmine if you start using this. I'm not saying to do that, but it'd be cool if someone did. From here, I've used all these. I've used all kinds of stuff to move stuff off the mainframe. Typically, I like to do it encrypted because I'm moving bad things off, like RACF databases, but you can use whatever you want to move it off once you find that port. That's it. Like we got 3 minutes left. I typically don't leave time for questions because I don't get good questions. But this audience had some great questions, so I really appreciate it. If you have any questions, or if you're, look, I'm up here advocating because the community for mainframe hackers is very small. There's like a dozen of us. There's like tens of us. So if this is interesting to you, if this is something that you're like, wow, I've never even thought about getting into this, please reach out. It's way easier now to get into mainframe hacking than it was 15 years ago. There's guides, there's whole YouTube channels. So if you're interested in this, please reach out to me. I'll be happy to help set you up and get you working on this platform. And thank you for having me here today at CactusCon. Are there any questions? Real quick, I got 1 minute. But I want the other person to have time to. Any questions? Wow. Thank you, everybody.
Do good for you. You know, all right. Hi, everybody. I'm Danny Quist. Can you hear me? Am I microphoning correctly? I can microphone even better. Is this better? How you feel back there, Adam? You're way in the back. You good? Okay. You can hear me, though, right? That's what I was asking. Okay, so I'm going to talk to you about reverse engineering Go. So just as a show of hands, how many of you have seen what assembly looks like in real life, like perhaps in a text file? Okay, how many of you have actually written the sacred language? Okay, good. So I'm talking to friendlies here, so we're gonna do that. If you find yourself lost, just kind of like pat your head or something like that, and I'll try to pay attention to the audience, and then I'll put it in terms of like dinosaurs carrying eggs or something like that. So I'm a little nervous about the technical content, so we'll go ahead and get started. Who am I? Currently, I work for a very small, very new startup called Unit 129. This is one of my first forward engineering jobs. Usually I'm a reverse engineer. So, you know, actually writing code is a lot harder than tearing it apart. In my past, I've been a reverse engineer. My specialty is weird malware. So anything new, I love, any puzzles, that sort of thing. I also do code author attribution, tell you who wrote it, and then if you need source code for binaries, I can extract it out. And I also teach a reverse engineering course at a university, and I haven't been fired yet, so that's it's been like 2 months. So past, worked at Redacted. That is the actual name of the company, and it is dead. So lots of sad memories. See some redacted people in the audience, so hello. Previous to that, I was at Bechtel, MIT's Lincoln Lab, and Los Alamos National Lab, and please don't judge me, I got a PhD. Okay, so what we're gonna talk about today is how to reverse engineer Go malware. And if you've ever, has anybody tried to look at a Go malware ever? Or any Go sample? Yeah, kind of a pain, isn't it? Yeah, nothing works. So I'll go through like my method about how I got it to work and show you just like a general overview. And then what we're gonna do is we're gonna talk about Beyond Leon, which is a ransomware group. And if you were here last year, there was an excellent talk on the tactics, techniques, and procedures, and all the network monitoring and everything like that. This is the add-on talk. And also, just as a side note, this is what happens when your company doesn't have a marketing department to shoot down talks, because this was supposed to be last year. But anyway, that's a little trivia. Okay, so what we're gonna do is we're gonna use analyzing malware as a practical example for learning how to reverse engineer Go malware. Okay. So here are my problems reversing Go. And if anybody else has any of things, please jump in. So most of the reverse engineering tools assume that the code you're looking at is written in C or C++, which is fine because most of it actually is. It's pretty rare that you find Go or anything else that's outside of there that comes in. Once you get into some of these languages, it's all about finding the libraries, because it turns out nobody writes their own linked list or their own dictionaries or arrays or hash tables, whatever. They all use the stuff that's built in. And so figuring out what is author written code versus library code is kind of the primary problem that we're looking at. And just to belabor that point a bit more, when you're reverse engineering malware, it turns out that they're, as a rule, very terrible software engineers, so they don't write much code. And so, like, when you do find their code, it's usually small and very compact and terrible. So, well, and I really shouldn't be too critical about that, too. You guys haven't seen my code, so maybe you have. I don't know. It's bad. So things like you wanna convert strings, copy them, convert from ASCII to Unicode, which is a pretty common activity on Windows, that sort of thing. Go does all of this. And actually any language, like if you could actually apply this to Rust if you're gonna be looking at that, or a Haskell program. There's basically no flirt identification. So you're kind of in the roll your own, invent the internet stage here. Furthermore, like any modern language, it does a lot of stuff for you. And by do a lot of stuff for you, it means there's a lot of boilerplate code you gotta skip over. And then it's also aggressively optimized by default. And things like types are not compiler constructs, despite the language implying everything is. And then compiler inlining is just, it's competitive and vindictive in the Go compiler. So you just gotta watch out for that as you're translating the assembly back into something that makes sense. I mean, really the problem is that Grismer, Pike, Thompson, those are smart people, and they wrote a really good language, and so now it's up to us to like try and figure out what's going on. Great. So what's the process? High level, we're gonna, whenever we're looking at a sample, this kind of applies to anything right here, but essentially what we're looking for is any of the strings. We want strings because that's what your APIs use. When you're opening a file, you do not pass it a base64 encoded text unless you're using some garbage thing like Java on a mainframe. Then maybe it does it for you, but for the most part, you have to pass strings to C APIs. You gotta get it. At some point, they're gonna wanna write an extortion note, because like in theory, they're trying to make money here. So like that's gotta be plain text. So there's gotta be some decoding and some actual plain text at some point. And so your job as a reverse engineer is either to just look at the ones that are embedded in the binary and draw conclusions, or decode them and then start to do the same thing. The next thing is that you wanna find the code that's actually written by the malware author. When we load up a Go binary, it's like 4.5 megs. And it's like 4.5 megs for just a hello world. It's a lot. right? And granted, that's like not stripping the executable, all the debugger stuff is enabled, and probably a lot of things that I should get out of it, but it's very big files. But most of that is actually library and runtime that's added by the executable. So you have to be able to identify those and eliminate it from your analysis. So how do we do that? And I'm kind of focusing on this as like you've never looked at a Go malware before and you need to like refresh yourself on how this works. This is just like my process for learning how to reverse pretty much anything. So you start off with easy mode. So we're gonna make a test program. We're gonna print a string. So basically you can do anything you want inside of here. You can read and write to a file, you can call a function, you can loop over a variable, that sort of thing. In the upper right-hand side, this is a little bit of an eye chart, but this is the Go code. This is garbage Go code, but it's just like a print thing. And all I'm doing is I'm just making a test executable that I can drag into a disassembler and see what it looks like. And the idea, and so this is how you compile it, I believe right here. And then the symbols here, when everything looks good and you're looking at your code for a very simple thing, you will find the symbols for something called main.main or runtime.main or not, sorry, not runtime.main, but like one of the, something that looks like the start for your program. And so this is a good sign. So we've basically put some things that we know about inside of an executable, and we're gonna try and learn and see what it looks like. So just looking at a Go executable as it's running and looking at strings, strings are the reverse engineer's crutch. But just on a normal one, you can see lots of things built in here. So there's a couple things that are interesting. The first one is this Go build ID. This is an identification string that's made every time you compile a Go executable. So this is a fairly good indication that you're dealing with a Go binary, because a lot of the internal Go stuff requires this. The next thing you'll see is a lot of strings that look like they come from standard libraries that have been inside of executables. So this is all normal. The way that Go works is that it builds up a string table. It doesn't necessarily have the null byte at the end of all strings. So what you'll see is them all flushed together. And so you'll see things like flags to various API calls, along with things like your command and control type stuff. The other thing to look for as you're compiling or looking at compiled Go binaries is that there'll be lots of strings inside of here. So as all of the libraries are linked in and the other runtime elements are copied in, it includes the file path. So this isn't anything that it needs to actually run, but it's usually included. So for my executable, this is running on a Mac with Homebrew, so it's running out of my directory up there. It encodes my directory in. And unless a malware author specifically goes through and edits the strings, there's not really a good way to take it out. So these are just some examples. So when things are going well, you'll see strings along these lines, and this is what it looks like. So when you get inside of a disassembler, this is what it's gonna look like. If you're wondering which disassembler it is, it's the best one. It's Binary Ninja. Ghidra is good because it's free. But if you get some money, get Binary Ninja. Their decompiler is the best, and Jordan is like much nicer than the other pro people. So that's my plug. I'm not being paid by them. I just like their code. Anyway, so if you've never seen assembly, this is what it looks like. There's standard calls. You can see strings inside of the executable. So you just pull it out. It looks pretty normal, and you read it like you would just normal API calls. There's a lot of like print lock and unlock. And then there's special things for printing strings and printing lines and that sort of stuff. But this is all boilerplate. Looking at the assembly, Go also seems to fetish moving around large pointers and XMM instructions for string copy, so be aware of that. So that's there. So it all comes out pretty straightforward. And if you actually use a decompiler, it does not look like garbage. So, I mean, there's a lot of calls that you would not see in normal Go code, like I had in the previous example, but it does a pretty good job of figuring out what the parameters are to functions, pulling out the strings. It doesn't do a good job of separating out all the Go string intrinsics, but really, who cares? I look at binary hex dumps all day. It's not a problem to pull that out. So this is pretty easy, right? Like if you get the code back to normal, you can just almost read it, provided you can read code. Okay, so just to start the process a little bit, or like to overview the process, we're going to start with a normal executable, and then you can start to add other programs. So there'll be some open source stuff. So pick a project on GitHub and just disassemble it, see what it looks like, especially if it includes libraries or links a lot of things, just to see how it does it. But what you need is like a set of gradually more complicated programs to lead you gently, step by step, through this, especially if you're recovering from COVID and have brain fog and that sort of thing. Having a real simple sample like Beyond Leon is a great way to start learning. Okay, so my recommended learning path, if you're looking at this, is to start out with the August 2022 backdoors and tools. This is kind of when they first came out. Basically, it was, the code looks like they spent 2 weeks writing code with a six-pack, or weekend writing code with a six-pack of beer. Is about the level of quality and complexity that it has. So it's not too bad, but like actually figuring out where the code you want to look at is the difficult part. There have been a couple of updates based on some events. The other one that I recommend looking at is the January 2023, so about a year old. That's a good version of that same tooling set, new versions of Go, and then recently the latest sample is actually it's actually quite exciting. These guys are not good at building tools, and so like they just discovered an obfuscator. So they're now using the Go garbled module to make things a little bit more difficult, but turns out those are hard to use too. Okay, so I stand on the shoulders of giants that have done a lot more work on investigating and looking into these people and tracking them down and doing a lot of the TTP investigations. I'm just a reverse engineer, the malware guy. I just want to say, recognize the work that Sean Patty and Hallie Shukai, I think I said that right, did last year with their Beyond Leon talk. It was excellent. I recommend you go back and look at that if you want to learn anything about how they operate and how bad they are at life. We wrote a couple blog entries about it, overviewing the initial Go execution that kind of dropped it out, or like got the actual IOCs out into the public, made them a little bit more aware, which brought some attention to them. And then Avast, the antivirus company. Does anybody here actually use Avast? No? No, I don't. Like, I don't. Right, maybe it's in Europe. Maybe I just like too American biased, but I just don't. Like, they do good work. Like, their analysts are amazing, and they wrote this decryptor for Beyond Leon that basically all you have to have is a copy of the executable and an encrypted file and an unencrypted file, and then you just go, right? It just like figures out the key and unencrypts everything for you. It's great. Excellent work. I just don't know how to give them money because I've tried to like buy their product and it's hard too. So if anybody has any tricks about that, please let me know. And then the next thing is we talked about how they've evolved after their encryptor got hacked, how they changed their tactics. But really, primary authors here are going to be Brad Pittick, Lauren Fivison, and many other shy people. So we'll get that out there. Okay, so what is a Beyond Leon? Has anybody been to Shenyang? Here's my theory. I think somebody went to Shenyang and said, hey, like, we got to name our ransomware gang, so what are we going to do? Well, those mask things were great. That's very hacker-ish, putting a mask on and hiding. Let's call it that. That's just my hypothesis here. I don't know if that's the truth. But it makes for colorful slide stuff, so you get to look at this right here. The key thing about this is it's Chinese theater, and I'm not the most culturally adept person, but they wear masks and dance and carry on quite a bit. It's supposed to be great. Never seen it, seen the pictures. So the way that they started out is that they started with they're a ransomware group with like super flexible ethics, like all of them. You know, hospitals, schools, those are all in scope. The way that they started is in June 2022 was their first victim. July, they started their leak site, and then they started just breaking into anybody they could with money. And the key thing that we noticed is that they looked really good at their initial access. Like they're living on off the land techniques, initial break-ins, everything was just like textbook, how you should do it, perhaps Perhaps it was a playbook they were following, put together by an organization that they used. Anyway, it was really good. Like, it looked like somebody had some training to this, and it looked like a very specific type of thing if you've had that training. Anyway, Cackle's got up. So they're really good at the initial access fundamentals. But what they're not good at is the other things that necessarily wouldn't be part of a operator team. So like managing the hosts and making sure the keys get recycled and that the SSL or TLS key or certificates get rotated periodically. All that stuff is usually somebody else's job, and they're usually not good at it. So that's there. So they break in really well. They accomplish the task. When they have their people, like their main people on it, they just get into the target and they do pretty well. The problem is that if you're running a business, you can't scale that. And this is a business for them. They're trying to like actually get money out of people. So we at Redacted, we started tracking them. Sean and Hallie's talk was much better at this. I'm just gonna hand wave over that part. But essentially we enumerate the infrastructure and we find the people and start to reverse engineering. Okay, so first victim, June 2022. Leak site starts in July afterwards. We publish a blog in September. Malware Hunter team has the first sighting of them openly in public, so I want to give recognition there. Shortly after that, like days after that, we published our blog and then pushed it out there and got that. But in between September and January, it was kind of good times for Beyond Leon. They were just making money. They're breaking into things. Their encryptor was working. People were having panic attacks. It was good times. But then the encryptor got released. You start to see weird, I wouldn't call them passive aggressive notes in the ransoms, but definitely active aggressive. They were very irritated that their stuff got broken, which I can understand. But eventually they had to just give it up. So like their encryptor doesn't work, they can pop it. And encryption's a big pain anyway, as far as the ransomware author. It takes a lot of time. So now they just steal data and then try to sell it back to you. So that's the other big thing. The other big tactic that they changed is that instead of doing all of the access and operations on target themselves, they started using affiliates. So we've started to see them advertise inside of some of these darknet markets, asking for affiliates to help them expand out their business and giving them a cut of the proceeds and all that good stuff. Standard malware operations. This is another Beyond Leon dancer if none of this makes sense. Okay, so the business model from the first part was compromise the target, install your tools for persistence, exfiltrate the data. Very important to exfiltrate the data first before you encrypt. This is pro tips for ransomware people here. Okay, once you do that, well, I guess if you have the key, it doesn't matter. But anyway, then basically you encrypt the data to force the conversation. You have the awkward conversation where you negotiate with people, and then all of the communication is done through this chat server called Talks, which is an open source encrypted system. Once payment is received, they would typically send you a decryptor executable, and then you could use that to decrypt the system. And has anybody noticed, like with ransomwares, how they're like oddly concerned about customer service? They're like, we will help you and handhold you through the entire decryption process and that sort of thing. And it's like, do you know what I'm upset about in this transaction? It's like, it is not that. Like, okay, anyway. Different cultures? I don't know. Probably should read a book and find out. But all right, so now they're on to single extortion, which is their stuff got broken. We'll go how it got broken, and technical details. Now they just exfiltrate data and threaten to release it. And this avoids having to do a lot of the decryption support, which was kind of weird to begin with. And now affiliates do most of the work. What this has meant is that instead of having just Beyond Leon tag tool sets, now other hacking tools are starting to come in and be tagged as part of the whole process too. So you'll see on some other reports from research places, I'm making some really awkward eye contact right here. They'll say that they're affiliated with other ransomware and malware tools. But that is not the case. They're just having affiliates in and other people are using their tools and bring it in. That's a pro tip. Okay. So what we're going to look at here are going to be the executable file artifacts. We're going to look at the backdoor, the encryptor. We'll look at how that got broken. And we'll talk vaguely about the decryptor and some of the listening posts. Generally from the code, this is written in the latest version of Go. Time of deployment, it looks like there's a CI/CD system. It seems like it's an Ubuntu 18 something system that they're using to build the executables. And what they do is that they build a custom executable for compromise. So when they target an actual organization, they'll custom build a piece of malware for you, which sounds a lot more ominous than it is. It's basically changing a text string inside of it, but it's good. Okay, usually Windows and Linux. However, fresh off the presses, I've got some Mac OS malware I got to look at when I get back to work. All right, so when you load a Go sample inside of your disassembler, the key thing that we're looking for are the symbols. So this is binary ninja, but don't worry, to make things confusing, I'm going to switch to IDA in just a minute. But what we're looking at is the symbols. And in both of these, all these tools, there are symbols that are basically like, here are the local variables, here are the functions that you're going to call, anything like that, like strings that will sometimes show up there. But really what we care about are the functions. The first sign of the problem here is that there are no names. Well, there are names, but they're like sub and then some hex stuff, which is not very helpful. And if you look at the executable, like there's no obfuscations. Like the strings are all there. All the APIs are there. It was basically just a bug in a lot of the disassembler tools. So what you have to do is that you have to learn about the Go internal format for building executables and then repair it. So, or you can just take some scripts. So what you're looking at is the Go PC linker table. Go PCLN tab is what it's sometimes called. This stores the internal names for variables, functions, anything internal inside of your function that you could possibly want to know the name of with a debugger or some sort of logger afterwards. So everything was changed. The only real difference between the malware sample I was looking at and some of the other ones that worked was the version. So the linker table had changed slightly. There was another field that I believe another field was added. So it was just a matter of getting that fixed. There were some very good, if you're looking for an explanation of how the Go PCLN tab works, their Sentinel Labs has a tool called Alpha Golang. These are a couple of IDA Python scripts that now work with the newer versions of Go. So all of the pull requests is submitted and everything, and they're still maintaining Alpha Golang, so it didn't just fall off into language, into nothing. So far right now, as far as the disassemblers, IDA Pro gets the gold star as far as reversing Go malware, just because it actually pulls it apart and makes sense of it. I would prefer this be binary ninja, but you know, writing disassemblers that support Go malware is real low on the product priority list for a lot of places, except for IDA Pro. Okay, so once you get the imports restored, what this gets you is like a lot of really nice things. So in Go, if you want to import a library, a lot of times you can just identify the GitHub repo that you want to pull the data in from. So in this case, there's this Cardianos, I don't know if I'm pronouncing it correctly, but it's a service manager for Windows. So if you want to write an executable and have it start and stop through the normal Windows process, you can use this. It's super handy. I didn't know about it before, but now I use it too. So like you do learn stuff from reverse engineering. It's pretty good. And then there's a couple of other things that are inside of there that are real interesting. There's this thing called MIMUX, M-I-M-U-X. And if you've ever done Go programming and you've ever looked at any sort of multiplexers, HashiCorp has one called YAMUX, Y-A-M-U-X, yet another MUX. Apparently they took it and modified it slightly so that you can arbitrarily execute code and some other things. The other big component that they make a lot of use of is this SOSO. It is a SOX connection and proxy server. So they use this for a combination both on their listening points to provide the SSL encrypted communications, but also to connect back and forward commands. So it's proxy aware. So anyway, like once you get the imports restored, this is what a happy import looks like inside of Go. We've got names, we've got main things, and especially what we're looking for is anything that says that it's like main related. And so once you get started looking at this, like actually reversing it, the negatives are that you get missing imports in pretty much everything, except for the later versions of IDA Pro. They do a little bit better job, but it's always going to be behind the curve. It's a little bit difficult to identify the author-developed code, but there's some tools out for that. The positives were is that the strings were intact, and then the imports, once they were rebuilt, it was just basically reading code at that point. So it was fine. So code extraction was possible, and that sort of thing. So once we got everything apart, we started to see some real interesting strings. And so I prepared this eye chart here so that some of you who are getting advanced in age, say in your 40s, you can use this as a reflection point about whether to go to the optometrist. But okay, that was a long explanation for nothing. Okay, so we got the Go build ID up top. That's important. It's probably a Go program. Over here, inside of each one of these programs, we have a lot of VCS identifiers. So like it says VCS equals Git. I know Git. I know where that's going. And it's got this revision. And it turns out that if you have an open GitHub repository, you can take those revisions and do this really amazing searching across the entirety of GitHub and find it. But wouldn't you know, if you have any private repos inside of GitHub, rest assured, they will never, ever disclose that to any authorities whatsoever. Like, they will not search for a hash for you at GitHub. So what I'm saying is that their privacy is really good. It's crap for doing these investigations, but everything else is great. But the VCS times inside of here seem to be pretty accurate. So this 428 is a very popular time that comes up. You also see lots of projects here. So in this case, the strings, it says that it's a home admin is where it was built. Thankfully, they didn't use their personal name, but they're calling it the socks, and then you can see that they have an out directory, and then they organize it based off of the IP address and port that the implant goes to. So each one of these things has its own operation. Over here, you can see that they have very, very poor judgment, and they're using snaps to build their code, which is generally not fashionable these days. But if we look at the other strings, we also see some of the compiler flags where we get all this. And you'll notice that none of these have any sort of commands to strip out symbols or anything like that. So everything is pretty much there. Looking at the assembly, this is where a lot of the internal configuration, like this is the internal configuration for a lot of these samples. I don't know if you can see this, but in a very odd, awkward read color, there's a address and a port. And over here on the left, we have an IP address and a port. And all these things are like super old, so they're not active anymore, but maybe somebody's hacking from the audience. So command and control is all routed through a SOX proxy. This is typically some compromised box that they have on a remote system. So over here you see an EC2 address. Other times you'll see DigitalOcean boxes. It's just whatever they can get a hold of and install their proxy software on to start doing this. And then typically there's some TOX communications that are there. So, but attacker issues commands and it forwards data over the connection. Can also send binary code to be executed. As we'll see here, this is a little bit awkward and not completely the complete side of the picture. If you want to look at the code loading capability, it is in main pointer program start. In this SHA-256 here, so you're gonna have to go on the YouTubes and look at pixelated stuff or email me or text me, whatever. But basically what this does is it downloads a blob of data, loads it into memory, and then executes it as a normal Go routine, but it's inside of here. There's also remote SOX control, so essentially everything is done inside of this main connect for SOX. This is the callback function that's in there. This gets swapped out if the binary is asking to do something else. All commands are base64 encoded, so they're pretty easy to decode and look at it, but there's not really much to see unless you capture the traffic as it's happening. Okay, so there's a flaw in the encryptor. And this was good because this encryptor, like, it seemed like it had a problem because you could do some cryptanalysis on it and see that like things weren't entirely random. So we were getting there, and I'm really glad Avast just like ran with this because they seem to have better crypto people. There was also a really great security scorecard blog post about this that actually detailed all the things you could possibly want to know about crypto and like why the problem was. But like at the end of the day, the problem is that they didn't use public key crypto. They used a static key inside of their executables, and that's how victims were able to pull it out. So there's a very good scorecard there, but this just basically broke them. And they were real mad about it too. It uses the Intel internal AES instructions, but none of this is all, like in software development, there's a couple of truisms that I thought were taken for granted. It's like, number one, I thought we got over our EBCDIC conversion thing, but like watching that last talk, it's nope, still here. And then number two is that you should actually never roll your own crypto. You should always use a crypto library. And if you can't use a crypto library, then steal somebody smarter than you that has done it correctly. And that's the technique that they chose here. Like they actually stole the code, we found the code that they stole. It's got the same flaw and that sort of thing. So this basically just took it out. And I don't know what the difference is, like why you wouldn't put the effort into like just making that correct. But my impression is that they're more on the operator side, like the reaching out and hacking into things skill set, not so much the making backdoors and implants, which is a definite different skill. Some people are good at everything, but not usually. Okay, so that was kind of where we are right now. They had a hard pivot. Nothing was working, or everything was pretty much working. Reverse engineering was basically looking for some static offsets inside of there, and then you could identify the code base, the set where it came from, and how it was going. And then the Beyond Leons got a little tricky. They started to apply some obfuscation, and they used this Go module called Garbler, or Garbled. Has anybody used Garbled before? Yeah, I haven't come up with it either. I haven't come in any mitigations for it, but I got a quick hack in. So what this does is it strips symbols out, it takes any of the strings that you might find useful and then encrypts them or encodes them, like encodes. And then basically makes it a little bit different. And essentially the problem that it causes you, the reverse engineer, is it makes it difficult to figure out who wrote the code that you're interested in, and finding that code is hard again. So we have no strings. Our crutch is gone. We're very sad. About to start drinking to get over this. But then we look at some research out of Germany by a very smart gentleman named Daniel Plomin. And I'm really sorry if I mispronounce your name. He might actually be watching the stream. But this is great. This is a thing called mcrit. Basically, it's a min-hash code research. Basically, it's a min-hash tool for doing fuzzy function code matching on executables. So without going into the algorithm enough for you to understand it, the way that it works is that it takes the mnemonics of the it takes the mnemonics of the instructions that are being executed and then builds a representation of the execution that way, instead of just looking at strings and hard-coded data offsets inside of it. It's great. He wrote a whole dissertation on it. Like, I can't do this in like 20 seconds up here. It's really good, and like it's readable. He's just the nicest guy. He's been super helpful. Like, he's even accepted my bad patches. It's been great. Okay, so this is good software. And basically what it's implementing is the min-hash and pick-hash fuzzy matching methods for identifying similar code. The idea of this is that you set up an mcrit system, you import all the common libraries and all the common sorted malware that you have. And then what you do is that you submit new samples to it, and it's basically like a cape or a cuckoo sandbox without the execution and that sort of thing. But then it tells you how similar things are. And so there's a couple of features that are very, very helpful inside of here for the Beyond Leon case that I'll go over. This is not like an expert usage of this, and it's definitely nascent and very very good, but I've had really good luck with it. Okay, so this is a MCRIT screenshot. So what I've done is I've uploaded every single Beyond Leon sample that I have, which is like 300 by this point, and then the brand new ones. And then what I'm trying to do is just figure out, can I identify what family they belong to? And so what's really nice is that right out of the gate, MCRIT does a pretty good job of identifying that this new sample that I submitted is an actual old, or is related to an old Beyond Leon sample, and it actually matches something like 3,300 of the functions. And then also it matches 3010 on the min hash, pick hash, and then it's also identified 2,200 of the libraries. So this is all great. It's all pulled this out, identified it. I can go and look at other samples to see if it's actually there and verify it, and it just saves me a whole bunch of time. And so if you have a new sample that's not being picked up by AV and you're like, WTF is this? It's a great way to get you in the neighborhood. Okay. The other nice thing about MCRIT is it does all of the library matching. So one of the goals that they started out with is that they wanted to have a more robust system for developing FLIRT signatures. FLIRT is IDA's fast library for identifying runtime or routines. I believe that's it. Anyway, function finder. So if you have a stir copy, it'll say this is a stir copy instead of you having to figure out like what that new XMM instruction is. It does all that for you. So it identifies it and it tags all the functions inside of there and makes it very good. So in this case, it identified the two libraries as MinGW, so that's the GCC compiler for Windows. A lot of functions were shared with that. And then the second one was Golang, which is another, basically the libraries that are added inside of there. So right out of the gate, we're able to strip out a lot of the content that was causing problems. Okay, so fast forward to January 2024. Looking at these, they're garbled. The strings are jumbled. They're hard to read, and I'm despondent. I'm in a bad mood. And then along comes MCRIT. And so I've already got all of my malware, or all of my old Beyond Leon samples inside of there. And I'm trying to like figure out number one, what component is this? Is it a backdoor, or is it a listening post? Is it one of the, the backdoors, or is it the actual encryptor, or something new? And none of that's in there. But what was really nice about this is that you can take that new sample that has obfuscations applied to it, put it into MCRIT, and then it gives you an idea of what you're actually looking at. So now that I'm up on the stage, I'm sorry, this is completely even unreadable for me. I'll post the slides so you can see it later. But allow me to hand wave it up here for you. Up top is my unnamed sample. So I didn't assign a family to it, so that's why it's identified like this. Turns out it matches great with another sample that's in the same set that I found. And then you kind of go down the list of shame here. And so we've got Win.Bandit, Win.Doja, and a whole bunch of these other things, and eventually we get to Beyond Leon. And you might wonder why all those other programs have been included inside of there, and it's for two reasons. Number one, they're using Go. That's one of the reasons. And then the other thing is that they're using a GCC variant to compile themselves, so they're being identified as similar. So already it's pulling out the tool chain and making that a little bit easier. Looking at the code, like once you get past all the obfuscations and you skip do all that, it's just normal. Like no AST changes have been made. The actual function and flow of the program is exactly the same. It's just the strings are garbled, and anytime you access a string, it's put in a decoder right before it, which is normal. So without any changes, we're actually in a pretty good place to be able to do this, to identify the code. And minhash and pickhash are pretty good algorithms for identifying these things. So we can actually go into a lot of the data or dive into it and actually look at the functions, because one of the things that you don't want to do when you're like actually comparing some of these functions is, well, you got to verify that they're the same. So what you don't want to do is you don't want to be verifying that there are two library calls that you're trying to identify, because basically what that means is that you're making a signature for a library call in the future instead of the actual sample. So there's a little bit of verification. It's got a very good method for looking at it, but what's really nice is on the screen, if you can see my little mouse right here, it's got a pick hash here. And next to it, you can see all the other malware samples and families that have been identified along with this. And so I can't, like, not really a good way to hover right here, but if you do, it's Beyond Leon. And if you, you can actually take one of those pick hashes and say, now what other samples inside of the corpus, and there's probably about 200,000 samples in the corpus right now, what other samples match this? And then basically what it did is that it'd be nice if it actually like said names and that sort of thing, but in this case it's like just the sample ID. All of these sample IDs are old, recent, like newly changed, pre-2024 malware, and then the new malware with like easily changes so you can see what's moved. Once you find that you have a sample, so in this case, I found one sample that was just leaping out at me and really going there. What you can do inside of mcrit is start to use this 1v1. So has anybody here used bindiff in the past? Yeah, it's pretty great, huh? Saved a lot of time. Made it like you're really trying to figure out how to productize that thing. But it just good. Like Halvar did just an excellent job with it, and then Google did as Google does and destroys things. Well, now I'm depressed. Anyway, mcrit works the same way. So it shows the perfect matches, which is what you want. It shows the slight differences where there's been some obfuscations, and basically gives you everything that you need. The only problem is that it's a manual process to convert between the two sample sets. So you got to copy some of the names over and that sort of thing. But that's just Python coding. We can fix that pretty easy. And so what you have now is that you can directly link and correlate samples together to be able to get that. So, you know, we took a unknown sample that had some garbled and obfuscation to it. It had nothing added to it. We ran it through mcrit, and now we have symbols that we can actually go and start doing our reverse engineering with. So check out mcrit. It's really great, amazing. Okay, so as far as concluding this talk, the Beyond Leon code base is actually fairly static. It does not look like they are doing development on it much at all, other than applying some obfuscators periodically. Binary diffing is basically how you combat somebody taking your strings away. Most of the changes occurred in 2022 to 2023, which really makes me seem like they had a developer then. But for now, like, I guess one of the open questions I have is like, you know, what was the big cause for the change to affiliates other than scaling the operation? And then how did that change everything? Also, look at mcrit and any other bindiff tools. There's a couple others that came out. Ghidra just released the NSA's internal identification suite, which it's still just amazing that any of that gets declassified at all. But it's excellent. I've had a chance to play with it. The only problem is it's garbage Java, so it makes you feel like you're writing on a mainframe. And then the Montreal, gosh, I'm having trouble remembering the name of it. One of the universities in Montreal is very big on reverse engineering as well, and they have a new binary diffing thing out at scale that works pretty well too. So go ahead and check that out as options, but that's how you reverse Go malware, or at least how I did this one. Any questions?
So yeah, this is Q&A portion. Yeah, it's a little touchy. We don't have anything on Discord right now. I'll check again in a few seconds. But all right, over there in the back.
Yeah, why does Go have its own procedure table?
So the question is, why does Go have its own procedure table?
Why does Go have its own procedure table? I'd imagine it's because they could have used the internal mechanisms for it, but I think by building their own internal one, they give them a little more flexibility as far as portable operations. But I'm just guessing. It does make it a little bit easier as far as debugging and finding those sorts of things for the PC table. But like if you're writing malware, it's actually a really bad thing to have all your stuff called out in this open environment. So it's like pros and cons.
Hey, guys, if you want to have a discussion, please take it out to the hallway. Yes, over there. What was the name of which tool, sorry?
The question was, what is the name of the bin diffing tool that was right after Ghidra? I believe it was McCabe University, but I think that does not feel right at all. I feel very awkward saying that up here right now. But if you talk to me and give me 5 minutes to Google, I can get you the answer to that. It's there. Is that good?
Anybody else on the aisle? So the three things for functional. Oh, so the three tables that are maintained. Yeah.
So the question was, and is the PCLN table, right? Is that maintained per function or the entire executable? And the question is entire executable is what it's typically inside of there. So there's probably a lot of nuance inside of the Go development environment, but everything that I've seen, it's program wide.
Anyone else? Okay. Thank you again. Morgan, I'm your MC for the afternoon, and we are going to get into AWS hacking and all kinds of fun exploits with John, so take it away.
All right, what's going on, everyone? You got a few seats down front here, some in the middle. Ken, I see you standing back there. You look very uncomfortable, so doing this for you, bud. Your brother's got a seat next to him, too. I don't know if you guys like each other well enough to sit there, but all right. So, anytime, bud. So, welcome, 60 Minutes, Hack This AWS Account. I'm going to start by giving a brief agenda, but more importantly, I want to kind of shill out the Absolute AppSec Happy Hour happening later. I'll hang out on the slide for a few minutes, so if you guys are interested in grabbing a couple free drinks, they said they were worried about hitting their liquor budget, so we gotta up their spend, and they said something about 3 sponsors this year, so there's a lot of drinks to be had later today at the hotel. So check it out, I'll be there. Ken will be there, already pretty much introduced him. So gonna quickly talk about myself, don't want to spend more than a minute on that because no one wants to hear me talk about myself. Give a little insight into why we're even talking about this, technical stuff, and then with any luck, Q&A. So we'll see how this goes. This is completely unrehearsed talk. I've never given this before. I'm excited about it. Timing could be a bit weird. So if I start speeding up at the end, it's designed so I can skip stuff that's less important. So that's good. Slides will be posted later this afternoon. There'll be a GitHub repo you can check out. More on that as we get through the talk. So who am I? This is a cloud security talk. Had to describe myself in Terraform. So if you've never seen Terraform, this is great infrastructure as code. My name's John Poulin, CTO for a company called Cloud Security Partners. We focus on cloud and application security, so do a lot of AWS and Azure pen testing, building cloud security programs, things of that nature. Before that, I worked for a company called GitHub, managed a couple product security engineering teams there, helped make sure the stuff that we were shipping was secure. Did a little bit of cloud stuff there, but focused mostly on the code. I'm from a small town called Bangor, Maine, way far northeast. It takes me a long time to get down here to Phoenix, but that doesn't stop me. This is actually my 4th presentation at CactusCon. First time was in 2014, I believe, so I've been coming here, every now and then for about 10 years. So why this talk? The title of the talk is Hacking AWS in 60 Minutes. So what's the relevance in 60 minutes? Well, I just kind of wanted to go through a speed run talk and figure out what can we actually do in 60 minutes to compromise an AWS account. First of all, it's really fun to theorize, to push boundaries, to see how quickly you can get work done. And then similarly, in the real world, as consultants, every engagement we do is time boxed. There's some amount of time we have to get things done. So who's to say that time couldn't be an hour? I've never had an hour-long pen test engagement, that's for sure. But still, it's fun. It's fun to theorize and figure out what we can actually do. And then the other side of things is attacks like this are already happening. I was doing an IR investigation recently, and we noticed that there was a compromised GitLab instance which led to a compromised AWS account. So doing the whole IR workflow, we saw that all of this happened in about 3 minutes, which was incredibly impressive for what the threat actor had to do. So 60 minutes may seem like an extremely short period of time, but with automation, it's pretty easy to get things done. So I wish there was a cool scenario to kind of throw at you all, like being locked in a data center or something like that, but I couldn't really contrive any cool scenarios that would benefit this 60 minutes type of story. But one thing that's worth recognizing is that in AWS and other cloud platforms, a lot of times the credentials that we gain access to are temporary credentials. And most often those temporary credentials are actually scoped for 60 minutes. So it kind of fits the story very well. If we were to gain access to a set of temporary credentials that last for 60 minutes, what can we actually get done? So for this talk, we're kind of focused on 2 primary things: pillaging data. So what can we find in the account? What can we steal from them? And then, can we gain persistence? And so to do this, we're going to be using a pen testing execution standard methodology. It's a pretty standard methodology that pen testers use. It applies well enough to the cloud as well. And so the way the rest of the talk is broken down is into these 5 different categories. So intelligence gathering, gathering information, vulnerability analysis, analyzing the information, exploitation, doing bad things with it, post-exploitation, doing bad things with the bad things we've already done, and reporting, which we don't have time for. So we're not doing reporting, not doing reporting in 60 minutes. And I thought it'd be appropriate to bring my AWS water bottle too, so I'll be sipping on that. Just water this time. So what is intelligence gathering? So this is the process of gathering information. So when we have access to an AWS account, we need to learn some stuff about it, right? Every account's gonna be a little different. So this is a process of identifying and enumerating account information. And it's the first stage to really understand what our target is. Not every time we drop into a cloud environment are we gonna know even what types of services they're hosting, whether or not they're hosting any applications. So the intelligence gathering part of the process is designed to help us find out that information. Now, one thing you will encounter pretty quickly when testing any sort of cloud service platform is that there are service quotas. So as you would imagine, this talk is going to be focused mainly around automation, right? You can't do a whole lot manually in 60 minutes, but you can sure do a hell of a lot, automated in 60 minutes. One of the things we have to keep in mind is there are service quotas. We can only send requests so quickly at these systems. And these will, in AWS, were formerly known as rate limits. They changed the terminology. It's called service quotas now. Sometimes that will vary by region, meaning you have quotas to send requests to resources in US East 1 and a different number to hit resources in other regions. And these service quotas actually can differ based on the account. So this isn't a consistent thing. And so when you're running tools, when you're running pen tests in AWS, you will certainly encounter timeouts. And most often than not, the tools that we're going to be talking about today are designed to handle those timeouts intelligently. But this is extremely important if you're scripting out your own tools or your own attack chains to be aware of these service quotas, to look for those and respond to them. And the other key factor here is intelligence gathering is iterative. Chances are we're going to be doing this step multiple times. It's an iterative process because as we gain access through the systems, we're going to be changing our level of access, we're going to be changing our roles, it's going to open our eyes a little more. And so we're going to have to perform this iteratively. Show of hands, who here has used AWS? That's pretty much everyone, but there's still some hands that weren't up. So when we're talking about AWS, there's two primary ways we access it. One is the web console, and then one is through the CLI, or the API. And so in this scenario, we need to think about, okay, we're compromising an AWS account. How did we get access, and what do we have access to? Do we have web console access, or do we have CLI access? Most often than not, access comes from leaked credentials or compromised systems. And so we're really going to be dealing with the API here more than the web console. And we'll touch on this a little more later, but just to kind of shed some insight, the web console, which a console for a web interface just seems like a bad name. When I think of a console, I think of a CLI, and I still haven't kind of grown out of that mindset. But console here is AWS's web interface, and we're normally logging in through username and password, logging in through SSO or some tools such as that, versus the CLI, which is command line or programmatic access. We're logging in through either access credentials or a role assumption, which we'll take a look at. So for the sake of this talk, pretty much everything we're going to be dealing with is the CLI. This is how most work in AWS gets done, primarily through the CLI. So the first major part of the intelligence gathering process is identifying targets. What's the useful information? What are we looking for, and where can we find that? So external network info, super important. If we can find DNS or IP addresses of system services that are in use in the account, that provides a little additional attack surface we're going to be exploring later. Publicly exposed attack surface, so having IP addresses is great, but if we can figure out what those IPs are listening on, whether or not it's public, looking specifically for ports 80, 443, any common web application ports, huge advantage. Users' permissions, knowing a little bit about the users and the roles and the permissions that are actually in use in the system provides a lot of insight that we're going to be leveraging. Secrets, obviously secrets are interesting to anyone. If we can steal an org's secrets, we're going to be able to use those to probably pivot into other systems, compromise other users, other roles. It gains a really large foothold into the organization. Code's another big one. Code is, in many cases, a company's most valuable intellectual property. So if we can walk away with their code, they're going to be pretty upset. And then in code, we find additional attack surface through secure code review. We find vulnerabilities we can exploit. We find secrets, because every organization has secrets in their code still. Not sure why that's still a problem, but it's still extremely common. And we're going to be looking in EC2 instances. These are where we're going to be storing code. Kubernetes clusters, S3 buckets, that's the file store. A lot of sensitive data being exposed there. RDS instances, which is one of Amazon's database services. A lot of sensitive information, user credentials, things of that nature, customer data. SQS queues, this is something folks don't think about. In a little piece of trivia, SQS was actually AWS's first service. A lot of folks think it was S3, but it was actually SQS, which was built internally at Amazon before they rolled out AWS. So this is kind of a cornerstone of a lot of microservice-based architectures. So SQS, if you can get a foothold into that, chances are you're in a trust boundary that the defenders have not expected you to be in. And CloudFormation is AWS's infrastructure as code solution. If you can gain access to the CloudFormation templates, you're probably going to be able to find secrets, find environment variables. If you can deploy your own CloudFormation templates, you've pretty much won there already. Cool. And Secrets Manager. This is an AWS service for storing secrets. If you can gain access to this, it's a treasure trove of information. So first, gaining access to an AWS account, you're probably going to need to figure out what the account can do. And you can run this AWS STS get caller identity command. It's going to return the account ID, username, and an ARN, which is the Amazon resource. I forget what it actually stands for. But this gives you a little bit of insight into the credentials you may have just gained access to. And then from there, we can use a tool called CloudFox, and we'll be talking a lot about CloudFox today, to describe the permissions associated with the user. When you gain access to an account, it's nice to know what you're able to do with it. So if you can simply go and list out the permissions, it's going to help you understand a lot about where to go next. Anyone used CloudFox before? I was hoping for more. Okay, 2 people, so I assume there's at least 5 in here. CloudFox, amazing tool. And maybe a little hard to see, but when you run that permissions command, it's going to go ahead and it's going to list out all the permissions associated for the particular user that we're looking for. And there may be some spoilers in this presentation. CloudFox is an amazing tool. The folks at Bishop Fox also released CloudFoxable, which is an intentionally vulnerable AWS account. So some of the screenshots here will be from CloudFoxable, so use that as you will. Hopefully it doesn't spoil anything, though. Amazing set of challenges there. Highly recommend that. And just to give a little link, you can find more about CloudFox on Bishop Fox's GitHub page. So finding out more about what the account can do, there's another tool that we're going to be using and talking about, which is Paku. Has anyone used Paku before? More hands on that one. I'm actually a little surprised. So that's interesting. Paku is another tool for mostly focused on exploitation of AWS accounts. It's module driven, so you can decide what types of modules you want to run. And this module in particular will enumerate the IAM permissions associated with the particular principal which you're connecting with. So you can run that, you can run Paku Who Am I, and it will show you the details and all of the permissions you have access to. So super interesting. It also, this is one of the major reasons I'm not doing a live demo, because it spits out your secret keys right there live. So kind of ruins the whole live demo concept. So yeah, another great first step to figure out what you're actually able to do. And again, Paku available on GitHub, Rhino Security Labs. Take a look at that. Highly recommend this tool as well. So in AWS, we've got some IAM concepts: users, roles, policies, and trust. So for those of you who are not familiar with AWS, access is given through policies. That's an example of a policy. Policies then can be attached either inline or actually directly attached to users, groups, or roles. These are all important things to know because they're potential nodes and edges for us to connect, our attack graph. Roles are actually an assumable identity, so these are a principal. We'll be talking a lot about roles as we go on, so we'll circle back to that. And then trust relationships. These define the principals, which can actually, in this case, assume a role. So we have this role called Alexander Arnold that has a trust relationship defined that says the principal CTF starting user can execute the STS assume role on the Alexander Arnold role. So that's how we kind of build the trust between roles and principals. And this is something that will be extremely common for anyone that's doing AWS pen testing. Super important to understand the significance there. And then identifying authorization details. So we can use AWS directly to issue commands to try to get a list of groups, roles, policies, etc. When you do that, there's a get account authorization details, AWS CLI method we can call. That returns a list of the details and a list of the policy ARNs, but it does not include the actual details of the policy. So just by looking at this, you really can't tell what this user is capable of doing. You have to go another step further and specifically view the policy details for a particular version of the policy. Really don't need to bring this up because other tools handle this automatically, but this is something that has confused me for years now. So just being aware that in order to view the policy details, you have to make another API call. And then, again, CloudFox comes into play. So CloudFox allows us to actually dump out a list of all the role trusts. So we see that there is a trusted principal that is allowed to assume a particular role. So in the Alexander Arnold example we came about, we very quickly see that, okay, the CTF starting user is capable of assuming that role. And then some of these are a little more challenging, like the role beard can only be assumed by the root user. So chances are that's not something we're going to be able to leverage right away during our pen test because we probably don't have access to the root user, and if we did, we wouldn't be going through a lot of this. So identifying network access. Network access plays another big factor into this. If we can connect to systems, we can exploit them. Regions in AWS, so US East, US East 2, etc. They are broken down into VPCs. VPCs have subnets. Route tables define the communication. Ultimately, we just don't have time to go through all this stuff. So what's the TLDR here? How do we figure out AWS networking in a very short period of time? So we use our tools. So fast mode, CloudFox, AWS network ports. This will dump out a list of the ports that are exposed in our environment and the host names associated with those. In this case, we have port ranges wide open to particular host running in TCP and UDP. We can run the Elastic Network Interfaces command. This will return Elastic Network Interfaces, which are attached to, in this case, EC2 instances, but could be attached to Lambda instances. These will include the internal IPs and the external when possible. Again, we're gathering information, so the more we can discover about an account right now, the better off. Internal IP addresses, still very useful. If we're able to gain a network foothold, we may be able to connect directly to some of those systems. But in 60 minutes, you're going to have better luck just attacking the external IPs. So super useful to get that external network info. And then another tool I recommend, Prowler, has a check built specifically for EC2 instances to find those which have allowed ingress basically from the world. This is an easy one to run real quickly and just figure out, okay, what can we actually connect to from our random VPN server that we're using. So Prowler, again, you can find it on GitHub. Another open source tool. They do have a commercial variant of this as well, which is pretty solid. So one thing that allows us to kind of speed run all of this and act very quickly is the fact that CloudFox and in a lesser extent Pacu, they track the loot for us. So as we're running commands or we're getting results, we don't have to worry about organizing that data or really consuming it at that point. We just need to run the commands, get the data, and let CloudFox track it for us. So inside of each of these files is going to be the output of the commands. But more excitingly, though, there's going to actually be data in them that tells us which commands we can run to exploit something in particular. So for instance, under bucket commands, what we can do is we can pop that open and we can look and find the command to exfiltrate all the data from the S3 bucket right there. Makes it super easy, super quick. You don't have to worry about putzing around with the AWS CLI to try to find these out on your own. Secrets, this is a big one, obviously. CloudFox allows you to run AWS secrets, get a list of the secrets, the name of them, the description when possible. Chances are you're not going to be dropped into an AWS environment that has access to listing all the secrets, but if you do, this is kind of an amazing place to be. And then CloudFox AWS CloudFormation will show you all the information about the CloudFormation stacks used. CloudFormation stacks, again, infrastructure as code. Tends to be a lot of secrets and a lot of information there. And so if we actually go and look at the loot for a CloudFormation template, you see it provides a lot of JSON, a little messy, but it shows us that we're using DynamoDB and something. We have some STS assume role going on. Gives us a lot of insight into the environment. But towards the bottom, you actually see a secret, which is a spoiler for the CloudFoxable challenges. And they even tell you right at the top, look here for secrets. Use something like Trufflehog, find some secrets here. Super common avenue. Code. Code is another big area that we want to explore. So where in an AWS environment can we find code? That's going to depend a little bit, but 2 places in the pipeline. So if folks are using AWS for CI/CD, they may be using code build as a pipeline. So we want to look there and figure out what that pipeline looks like. Where are they getting the code from which they're building? Do we have a way to gain access to that? So we can use CloudFox to gain information about code build. ECR, Elastic Container Registry. Folks are building these Docker and container instances with code on them, publishing them up to Amazon's ECR. So if we can pull those down and start exfiltrating their code from their container instances, that's actually a vector that's very commonly overlooked. And then on disk, systems are running applications. They're going to have code on them. So ECS, which is Elastic Container Service, we can take a look at the ECS tasks to find out what their task definitions look like, which container instances they're using, and we can kind of work backwards from there as well. EBS, so EBS are basically the storage drives attached to EC2 instances, which is AWS's VMs. And so we can actually look at those storage volumes, and we can look and pull down the code from those by remounting them. So Pacu has a module called EBS enum volume snapshots, which will go ahead and look for any volumes that you have access to mount. Once you mount those, you can exfiltrate the code and anything that's on them, including secrets. And then Lambda. So Lambda is functions as a service, super common to use, especially in cloud-native companies. A lot of folks are deploying Python and Golang code through AWS Lambda. So we can hop over there, we can take a look at what functions are available, we can rip those down very easily, and then we can do some code review on those functions. Functions as a service running as Lambda, they have vulnerabilities too. So they're consuming data from places, so if we can tamper with or force them to ingest data that we're giving them, that's another pretty commonly overlooked attack surface. And so remember to review the CloudFox loop files. Super valuable. That's going to have all your information. You can run all these commands I've given you in like 30 seconds, but you're not going to have time to process that information, right? So you need to review these loop files at some point. So public or accessible EBS snapshots. We just talked about EBS snapshots from a code perspective. Folks often overlook that EBS volumes can be made public. This doesn't happen too often, but providers like AWS or Azure, they like to host virtual machine instances for people to use. That's common for them. But myself, as a consumer deploying services in AWS, chances are I'm not deploying things that I want people to be able to use publicly. So there's a Prowler module that you can go out, you can run, and you can look for publicly exposed snapshots, because an attacker can grab those snapshots, remount those, and then run away with all of the data. There's a really good DEF CON 27 talk, I believe, DC 27 talk, finding secrets in publicly exposed EBS volumes. There's folks out there who are automating this type of thing, looking for EBS volumes to pop up on the internet and exfiltrating secrets from them. So highly recommend taking a look at that talk. Again, finding secrets in publicly exposed EBS volumes. And similar to Prowler, you can do the same thing just with AWS CLI, nothing special there. So word to the wise, we could spend all day doing information disclosure, or information discovery rather, but again, we only have an hour in this theoretical environment. So using automation, we should be able to run all of this in about 5 minutes. And then from there, we can focus on actually analyzing that data. Leveraging automation is key here. And most likely, we're going to have to return back to this, this part of the process, because again, it's iterative. So we're going to move on to vulnerability analysis next. So now that we have a bunch of data, what can we do with it? What's interesting there? And to be honest, in many cases, when you gain access to a cloud environment, you may not have a ton of information to go off of. That's a sign of a mature and well-architected cloud environment. So if you don't have access to even gain any information about it, they're doing something well, and you may just have to be a little more patient. So bringing this up because you may not have any data to actually analyze here. So finding easy targets. Looking for things with port 80 and port 443 exposed is generally a treasure trove, because you can find targets that are publicly accessible and are outside of the typical cloud native solutions, which means they may have more vulnerabilities for you to tap into. And so looking at a list of the environments, we can do that with CloudFox. Looking for things with port 80 and port 443 open is going to be super valuable. And the reason I even bring this up at kind of the first stage of the vulnerability discovery process is because once we identify targets that are exposed, web interfaces, we basically want to throw them over to scanners, fire them off. Again, we only have 60 minutes, so we don't have time to go actually fuzz these applications ourselves. But if we do it first stage in this process, we'll have at least 10 minutes or so to allow the scanners to run to try to find any sort of attack surface. I'm talking both web-based and host-based scanner. So I love Burp Suite Enterprise, throw Burp Suite or similar tool at it. But in the same sense, throw Nessus at the same server will identify things that Burp Suite would not. I actually have a lot of success running Nessus and other host-based scanners on web apps, finding things that other web app scanners don't even find, which is pretty incredible. And coming into this with like a tuned scanner is super important. So there's some vulnerabilities that we are interested in, and there's some we don't care about. So why waste time scanning for the things we don't care about? Things like remote code execution. If we can gain remote code execution, we can do a lot from there. That's kind of our ideal vulnerability situation. Server-side request forgery we'll talk about in a little bit, but that may give us access to assuming a role which will allow us to escalate our privileges. HTTP request smuggling can be used to bypass a lot of security controls, a lot of WAFs, so that's a pretty valuable one. And then I always like to look out for path traversal and authentication bypass. These can land you some really good results, especially if you find like an F5 load balancer in the account. Those things have had a tough 6 months or so with unauth RCE vulnerabilities and things of that nature. So if you haven't patched your F5s, you're in trouble. So again, other vulnerabilities, while a cross-site scripting vulnerability is extremely valuable in the real world, in a 60-minute time box engagement, not going to have any luck with cross-site scripting. Don't bother looking for it unless you really, really don't have anything else to go off of. So ultimately, to summarize, we're looking for vulnerabilities that would give us operating system or file system level access. Then from there, we can pivot. Most exploitation is going to require some type of role assumption. So chances are we're going to gain access to some principal or some role. It doesn't have access to do everything we want to. So we've got to work on assuming other roles. So this can be done in two primary ways. STS assume role, you pass in the role that you want to hop into, and you pass in, you need to give it your profile or whatever credentials you want to use to get there, and just give it a name. Not a huge fan of this approach. I prefer actually using the AWS credentials file. We can wire that up, pass it the role ARN, give it a source profile, and say when we tap into, in this case, the Ramos profile, we actually want to, behind the scenes, assume the role that we're defining there using the profile that we're defining. So much quicker way. You don't have to worry about juggling, temporary credentials or anything like that. AWS CLI will handle that for us just by wiring it through the credentials file. So finding roles of interest. We want to look for roles with significant privilege. So things like EC2 star, IAM star, this would say, hey, allow the principal to do anything with the EC2 service or the IAM service. Still pretty common, unfortunately, to find overly privileged roles in this nature. So anything with a significant privilege is going to be valuable. Alternatively, we can look for roles with a specific privilege. So one common attack technique I like to use is trying to spin up an EC2 instance. So if we know that's what we want to do, we can look for principals that have the EC2 run instance command in particular. With run instance, we can boot up a virtual machine. We can use that to target other systems. We can do some internal network fingerprinting. So it's a valuable attack technique. And understanding the roles kind of helps us plan our attacks. We may get to this point and find, okay, there's no role of interest to us here. We can't do anything with this at all. So at that point, then you need to go back to your information discovery, see what you may have missed, and it just could be, again, that it's a well-architected account and there's really not much you can do. So at that point, maybe your vulnerability scanners will come back with something useful. But again, building our plan of attack here. And then moreover, with roles, I recommend Principal Mapper or PMapper. This is a tool that will analyze permissions and build a graph of those permissions. Once we have a graph of permissions, we can then query it to look for things that we're interested in. And when I say permissions, we're talking about IAM permissions, but we're also talking about things like bucket policies. So it combines multiple different sources of rule engines to figure out if you can access a particular resource, for instance. So the first stage here is, call graph create. That's going to go out. This can take a while, especially in a large account, because it's building a pretty large graph. And then from there, we can issue queries. So in this particular example, the query is who can do EC2 run instance? And it's going to go out and query that graph we've already built and look for paths to get to EC2 run instance, if that's our ultimate goal. We could also do who can do IAM create user, for instance. So any AWS permission you're interested in, you can query for. And more exciting, it supports visualization. So if you're a visual learner, this is super useful to figure out which roles are connected and how they're connected, because this shows you very clearly, if I'm starting as that CTF starting user, I can then assume the Christian Pulsic role, and then I can assume over into another role there. And then from there, we can just keep bouncing around. So super informative. Principal Mapper built by NCC Group on GitHub. This project's a little bit stale. I don't think there's a lot of active development going on, but it's still extremely valuable. CloudFox does a lot of the same functionality, but they actually recommend running PMapper and then having CloudFox consume the PMapper output. So that's why we've got to have a pretty big toolbox for this type of stuff. Misconfigured S3 buckets. S3 is a huge source of data, particularly in customer data. So we can run CloudFox AWS buckets to get an inventory of which S3 buckets are available. we can then try to identify S3 buckets that we can access either through our role, so things that we specifically have access to, or things that are accessible to the world, which is a bad situation in most cases. But more interestingly, though, is we can use that PMapper graph we just created to issue queries to figure out who can actually do an S3 Git object, which is how you would download a particular file from a bucket. So if there was like a prod credentials bucket, we could issue a query and say, hey, who can actually access that to pull down the credentials? So super valuable. And as far as data that we're looking for, again, with 60 minutes, it's really hard. You're not going to have time to pillage a lot of data from S3. Things that are interesting to me, any sort of sensitive data. So if you saw there was a bucket named customer data, customer logs, anything that may look like it's production, those are kind of what I would tailor myself to looking for. Source code, again, another valuable one that would be pretty quick to download. And then application logs. If you can download even a sample of the application logs, you're going to be, most likely you're going to be able to gain access to some secrets and then some insights, maybe some stack traces, things that will help progress further. So really looking for any sort of data that can support exploitation when at all possible. And then kind of a last-ditch effort, run some additional tools. I recommend Scout Suite and Prowler. We've talked about Prowler a bit already, but Scout Suite in particular is a cloud security auditing tool. Outputs an HTML report, which is really nice to kind of walk through. Tells you, hey, these are the high-risk findings. If we're in a very time-boxed situation, we're trying to exploit something, we can just dig into the high findings, see if there's something that we could actually try to exploit. But again, these are kind of last-ditch effort types of situations. Prowler, on the other hand, Prowler also has an HTML interface. They've got JSON and CSV exports, which I think is a little more valuable in many cases. They have more checks and more support. With the caveat there being with more checks, it tends to be a little slower. So there's a good chance you're not going to be able to completely run all these Prowler checks in 60 minutes alone. So you really want to kind of fine-tune those a little bit. And then with any of this tooling, you're going to be blowing up their CloudTrail logs. So there's going to be a lot of data. So if you're trying to hide under the radar, that's not going to happen with any of this stuff. So worth really calling that out. So at this point, we've kind of run all of the tooling to look at any of the vulnerabilities we can find. Obviously, there's more vulnerabilities in the cloud environment that if you had more time, you'd want to exploit or want to take advantage of. But in 60 minutes, we're kind of looking at very specific and niche areas. So given what we know already, do we have anything we can actually exploit to go further? If not, again, go back to the beginning, start over. A lot of cases where that's going to be the situation you end up in. So exploitation. So the first thing you really kind of want to think about is privilege escalation. So knowing what we know about the environment, can we escalate our privileges? If you're already dropped into a high privilege user, you probably can skip this step, right? Because you already have a lot of functionality. So if we're able to find roles or policies that have lax trust policies, we can try to assume those roles to escalate our privilege. If we find roles that have the IAM pass role or EC2 run instance, this combo is super important because we can then spin up new EC2 instances, tell it which role we want it to use, such as the administrator policy attached role. So a lot we can do there. A lot of good references online to kind of dig in more onto that side of things. But again, PMapper kind of comes to the rescue here because there's a built-in query for privilege escalation. We can just run that with PMapper. PMapper will look and try to find ways that we can escalate our privileges. This is quick too, very, very quick. And then assuming we're able to, then we just kind of roll hop, bounce around between those roles and then continue the process. And then, post-exploitation will be a little more exciting in this particular case. And then one other option I like to recommend is the S3 pillaging. If you find yourself attached to a role or with the permissions to call S3 get object, that's when you know you can start downloading stuff. You can start pillaging things. If you have access to S3 list bucket, that means you can list out all the contents in the bucket, and then you can start recursively downloading everything in there. So it's possible to have only access to download without access to list, and that's when things get a little more challenging because you don't necessarily know what content is available to be downloaded. So with these two, it's kind of like the holy grail of being able to exfiltrate from S3. And AWS makes this easy. You don't really need to use any additional tooling. You just call AWS S3CP, pass in the bucket, the path to the bucket, and to the folder that you're interested in, and then tell it to do it recursively. This will take a while, though, so your mileage may vary on that one. And then once you start downloading stuff, the next thing you kind of want to think about is what can we do to find useful information here. So scanning for secrets is a good one. We can run TruffleHog on that file system. I always recommend no verification. So if folks aren't familiar with TruffleHog, TruffleHog is a tool to find secrets. And by default, when it finds secrets, it's going to make calls to those third parties, and it's going to try to verify or validate that those secrets are actually legitimate. So you don't always want that to happen. You don't always want it to go out and say, hey, we found this AWS secret. Can you tell us if it's legitimate? Because that's when alarms start going off. So yeah, I always recommend no verification. And in this case, focus on cloud provider credentials. So we're working in AWS. Any AWS credentials we could get would be great. Hybrid cloud or multi-cloud are common things. So you may very well find a pathway into GCP or Azure just by looking through credentials. And the other thing I didn't mention is I would also look for GitHub and GitLab credentials as well, because if you gain access to those, you may be able to gain access to CI/CD systems that are deploying the infrastructure. And then you have a lot of attack surface there. And one other thing to keep in mind, and this is often overlooked, but S3 buckets by default don't log when someone accesses a particular object. So if you're trying to be stealthy about your exfil, there's a good chance you're going to be able to download everything in a bucket and not have them notice it, because again, this is not logged by default. And a lot of companies don't enable this level of logging because it can be pretty expensive depending on the size of the account. So keep that in mind if you're in a defense situation. So yeah, TruffleHog, take a look at that on GitHub as well. Great tool. Secrets pillaging, obviously, if we gain access to a role that has the ability to actually get secrets or list secrets, that's kind of like a holy grail. Pretty unlikely in most modern cloud systems because AWS makes it kind of challenging to actually go out and make this type of mistake from a IAM perspective. But again, we can just rely on the AWS CLI to gain access to those secrets. CloudFox Loot, when we tell it to find all the secrets, it'll actually give us the commands to go out and exfiltrate those secrets, assuming we have the permissions as well. SSRF, another big one. So if we've been able to encounter an SSRF, server-side request forgery vulnerability, in an EC2 instance, we can actually exploit that to make a call to the instance metadata server. And with that, we're able to ask it, hey, what role is attached to this instance? Not all instances will have roles attached to them, but if they do, what that means is we can actually go in and we can assume the credentials that are attached to that particular role. So it generally takes 2 API calls, one to get the name of the role that's attached, and one to actually go out and access those credentials and assume that particular role. So if, for instance, we've compromised a server that had a trust with S3 and was being used to upload data to S3, well, with an SSRF vulnerability, we can go out and then we can start making calls to S3 on behalf of that server. So at this point, this is where I'd lean very heavily into Pacu, because again, it's focused on exploitation, which we're on the exploitation phase. So using modules for escalation, exploitation, lateral movement, a lot of ground to be covered there very quickly. And very quick primer in how Pacu works. You fire it up, you tell it to import some keys from your AWS profile, and you tell it to run a module. and there may be a dependency on other modules. It's going to help you get through that and say, hey, we need to grab this other data before we do this. So in this particular module example, System Manager, RCE, EC2, you can fire that off. Paku's going to look through your EC2 instances, find ones that have System Manager installed, and try to use your profile to gain access and execute commands. So highly recommend looking through the module details page on Paku Wiki. There's a ton of exploits there. It's actually pretty scary. And so we're running a little tight on time here. So diving into the last section, post-exploitation. Given 60 minutes, I don't know how much post-exploitation we're realistically going to be able to do, but there's a couple of things to keep in mind. Expanding access and building persistence. So if we are time-bound to 60 minutes because we gained access to credentials that last for 60 minutes, one of the first things we may be thinking about is how can we make those credentials last longer? What can we do there? So there's one technique called role juggling, which if you have the ability to run IAM assume role, you can take your temporary credentials, assume another role, and when you assume that second role, it regenerates the credentials and gives you a new time window of 60 minutes. So if you know that's what you're up against, you just keep role juggling relatively frequently, and you'll have prolonged access. Avoiding access key removal. So if you're caught, if the detection team finds out you're using some credentials for nefarious purposes, they're going to revoke those credentials pretty quickly. Well, if you use the STS Git Federation token with those credentials, you're going to gain access to a second set of credentials which are not removed when those access keys go away. So you could buy yourself most likely another hour of time by following that methodology. CrowdStrike has a really good blog post on how to actually exploit that. And then one other technique you can use is to try to pivot to the AWS Web Console. Most often the Web Console is the same as the CLI from an access control standpoint, but there's some nuance and there's some things that are different there. So if you have access to a set of system credentials, access keys, you can use AWS Console or AWS Vault to take those keys, then gain access through the web interface and play around with that as well. And then with persistence, kind of the obvious solution is, hey, I'll just add another user or modify a user so I can just hop in through them. That's kind of obvious. Defenders are looking for that. You'll be detected pretty quickly. If you have access to modify or attach policies to a user, to an instance, that's another good way and a little more challenging to actually detect. Another common technique you'll see is backdooring instance data in EC2 instances. So if you are able to write instance data into an EC2 instance, whenever that instance boots up, it's going to execute whatever shell command you give it, and that could be a C2 or some phone home giving you access back to that account. And then one other situation I don't see really very often, but Lambda instances can be fired up with roles. So if you're able to modify or inject malicious code into a Lambda function, or you find a vulnerability in a Lambda function, you can exploit that to gain access to the role that's attached to that function as well. And again, this is where Paku comes into play again. Paku is really solid for both exploitation and post-exploitation. So if you're really struggling to gain persistence into an account, leverage Paku. Chances are if Paku can't do it, you're not going to be able to do it. So highly recommend looking at that. And so with that, I will take some questions. I tried to call out some resources there, but I also want to let folks know earlier I just published a script that automates all of this stuff, so you can give it a try. GitHub.com/cloud-security-partners/hack AWS in 60 minutes. So it's fun watching that work. That's how I escalated my privileges without even knowing I was going to do that. So you can get in some trouble there. All right, anyone have any questions? Easiest Q&A all day. Thank you.
persistent scams. And here to guide us through that is Or.
Thank you very much. So I will introduce myself briefly, and that will enable us to better understand what the story that I'm trying to tell here and what's the research behind the story. So, as mentioned, my name is Or Katz. I work for Akamai. Doing this research, my title was Principal Lead Security Researcher. Recently, I moved into the product management space. Hopefully, that will be accepted well here today. And part of my work during my career was to do security research, but in the context of working in a security company that has some challenges with defending our customers and building security products. So that's my point of view on some of the things that you will see here today. We'll talk about some storytelling, which I find interesting, and you might find that as well, that tell about some of the challenges that we have out there when it comes to phishing from a defensive point of view, right? Not from a consumer point of view and the thing that consumers need to do or can do or should practice, but more from a vendor point of view that try to build a security product and need to face some of the skills and the challenges out there. So the title of my presentation is The Story of a Never-Ending Scam, Phishing Scam. But there is an alternative title to this presentation, which is When Natalie Hamilton Reemerged with Vengeance and an Empowered Driller. Okay, so you'll probably ask yourself at this point of time, who is Natalie Hamilton, right? Because that's an interesting question that we need to address. So these are the things that I know about Natalie, and I hope that you will know her as well by the end of the first half of this presentation. And she will help us in a way to tell the story that I'm trying to tell. So what I know about Natalie, right? She likes quizzes and winning prizes. She now owns new smart TV, vacuum cleaner, 2 backpacks, and a power driller. When she sees Survey, she's getting flashbacks, and we all. She has an amorphous kind of appearance, and we talk about that as well. And she hasn't taken multiple choice tests since college. Really interesting. But before going and introducing Natalie and some of the stories behind Natalie, so how did I ended up here today? So I would say over a year ago, like a year and a half ago, toward the holiday season, I got an email. And I will not focus on that, but that's an important thing for you to know. I got that email to my Gmail account. It was not classified as spam. It was on the inbox from my Gmail account. And again, we'll not go through that and explain why it got into my inbox account, but let's keep it as is. And that email tells the following story, right? So there is a kind of a survey, and if you press on the link, and we'll redirect you to some website, and you might win something as a result of that. And the thing that was interesting at that point of time is, and before that, the reason that I was getting that, or in a sense, was able to see those kind of attacks, is that there is a lot of those attacks. It's not new. And when I saw it, I was not impressed, really. But I was a bit impressed, or I thought to myself, there is some interesting thing here, because it was a bit branded toward Halloween. And I asked myself, well, something spent a lot of time to do that, so worthwhile for me to look into that. So I looked into that, and it's a well-known scam that I saw for years now. And that scam tells the following things. So step by step for the scam. Step number 1, you're getting an email. Once you press the link, you are landing on a malicious website. That malicious website is telling you need to answer some quiz, and if you will answer the quiz, you might win a prize, but actually everybody are winners and everyone allegedly win a prize. And in order to get that prize, which is a cool prize, you just need to pay for the shipping of that prize, right? And when you need to do that, that results with a couple of things. First of all, you might say, hey, well, I want something that's worth $100, and if I need to pay for phishing $7, that's okay, right? It's still a really cool price. But more to that, once you pay for that shipping, you're giving away your credentials, and that's a problem, right? And that's the issue. But it's a more tricky kind of thing because when you give away your credential, adversary have between 5 to 10 days to do something with that credit card, right? Because you're expecting to something, you will probably not report that, and that gives them a grace period to do something wrong with that stolen credit card number. Now, how I met Natalie, right? That's the question that needs to be answered. And I met her because once I was going into that website and I was scrolling down, I was able to see some sort of a user experience or like user testimony kind of dashboard down the website. And one of the images or one of the person that appears in that website was Natalie. That was the first time that we met. And as you can see on screen, that's her testimony. She's saying she haven't taken multiple choice tests since college. So when she saw the survey, she had some sort of a flashback to the school days, right? So that's our first time that we got acquainted. And right, this is, I read that one. So that's the one of the information that I was able to learn from her. But the funniest thing is that I was going over that scam and trying to use some of my experience and some of the techniques that I had, and I was able to see a lot of those kind of attacks, but each time I was able to see Natalie reemerge again, so all those 3 examples are Natalie with the same name, the same text, one by one, different images, right, because it was different campaigns or different prices being offered, right, and obviously she's not the same person, right, so that's her amorphous kind of appearance in a sense. Now, that happened, and I wrote some blog about that, and it got published and got really nice attention out there. And a few months later, I got another email with the same kind of concept, the same kind of scam, and I was searching that scam or working on that scam, and I was able to see that Natalie reemerged again, but this time offered me a power driller. Now, when I refreshed that website, the same website, each time I refreshed that website, I was able to see Natalie reemerged again with a different picture, with the same text, and with a different image of that power driller being offered, right? So someone, well, working very hard to make sure that the scam works, that it looks genuine, that it looks legit, right, as much as possible. Now, to be honest, I'm not here today to talk about Natalie or that scam in a sense of it's not that unique, that scam. So what is the story that we are here today to try to explore? So one version of that story is the campaign, right? And in our case, it's a very invasive, high-scale, very persistent kind of scam that runs for months with hundreds of thousands of victims, right? And I will go through some of the social engineering techniques being used, anti-detection techniques, and abusage of web services, okay? So that's one take of the story that we are here to see today, but there is a different kind of thing that when I was doing that research caught my eye and motivate me to do that. And that's the issue that, right, we are talking about phishing for 20 years now, right? So the question needs to be asked, how come after so many years of phishing exists as an attack vector, how come it still works? How come it's still effective? How come threat adversaries still continue to do whatever they want to do, right? And they are probably here to stay, and unfortunately, that scam is still working. That's the question that I had in mind. That's the question that I will try to address here today. And the answer won't be easy. Won't be easy to us as an industry, and as a person that works in a vendor that try to build solution, the answers are pretty much hard to get. We need to work harder, and we'll talk about that. So let's start with those techniques and things that were used in that campaign for us to understand the level of sophistication and to understand what we need to deal with and why it's a bit challenging sometimes. So when it comes to social engineering kind of techniques that we're able to see, we were able to see that it's a scam is really, really trustworthy, meaning it's really, really built well. The design of the website is well defined. It looks really genuine. The price and the deal being offered is not under the category of too true to be true, not too good to be true, sorry. Meaning it's a nice price, but it's not like a car, right? Or $5 million. It's something that create engagement and create an attractive kind of deal for those that might fall into that scam. There is a sense of urgency in those kind of things. As you can see on the right side of the screen, there is a clock that's running down and trying to engage the users or the potential victims as much as possible. And there's the fake user testimonies that we saw before that create, again, a level of trust. Adversary goal is to create trust in that sense. Trust lead to more engagement lead to more credit cards that are being stolen. So that's on the technical, on the social engineering side of things. But when it comes to the technical element being used in that scam, and again, bear in mind, this is a widely distributed, very volumetric, well-known kind of attack vectors that was hitting a lot of users out there, according to the feedback that we were able to see and according to the numbers that we had in that sense, and we'll see some of those numbers. So the first step in that scam is that scam created some sort of a network that enable adversary to create those phishing attacks and make sure that they are not being detected or the time of detection takes much longer. So the first phase or this initial step in that network was the initial link step, right? And what does that mean and what are kind of the techniques were used in that context that create a bit more challenging situation? So the first step of the link that being delivered in the email that got into the inbox include URL shorteners, right? So you can use public URL shorteners, which is a well-known technique. But in that case, and that case is very similar to that, we were able to see a bit more sophisticated way. So the adversary were using LinkedIn shortener, meaning they opened the LinkedIn profile, uploaded URL into that profile, and as a result of that, got from LinkedIn a shortener that is associated with LinkedIn. So you might ask yourself, so what's so sophisticated about that? It's not that sophisticated, but from a defensive point of view, when you're trying to detect malicious links, and you look into links, you use their link's reputation. And if the reputation is legit, and if that's a well-known website that create those shorteners and known to be good in most cases, from a defensive point of view, it makes our life a bit more harder. The second part of the second technique that we're able to see is that adversaries were using web services, well-known, widely used AWS, Azure, and GCP services to create sort of a redirection capabilities. Again, the same motivation, using a well-known infrastructure that's known to be in most cases good, create a more challenge for us to go over those URLs and try to make sure if they're legit or not legit. One of those kind of links being used is the following one. So I want to emphasize that because we'll talk about that example as one of the techniques being used to make sure that the attacks works well. So we have the first part of that colored in blue, which is the subdomain of, in this case, Windows.net hosting services. So that's the customized subdomain that's associated to the adversary that opened a service on that kind of website. The second part of that URL, you can see a red hash value, and afterwards we see something that looks like a token. Question, what happened once I press a link to the value that appears beyond the hash value? Answers? Or let me ask you like that. Sorry? Well, yes, in a sense, but in a technical context, what happened on our browser, or what happened from a network point of view once we press the link? So from a network point of view, once we press that link, the value that appears beyond the hash value, the hash sign, is not being sent to server. That's a value that can only be retrieved by our browser, by JavaScript running on our browser. And that's an important notion for us to know. So the second step, or the second phase in the network, is a routing and filtering capabilities. And here we were able to see a lot of kind of techniques being used to make sure that detection long-lived and not being detected. using geo-filtering and customization, meaning if you pressed on a given link from a given geo, you would go to a given website, and if you press that link from another geographic location, that will be redirect you to a different website, okay? More to that, some locations, geographic location, were blocked. From an adversary point of view, they want to make sure that only victims will go through the networks. If you are not a victim, that's probably something that they want to avoid, because you might be a security researcher or security analyst or vendors that try to think and go through those URLs and figure out if that works or not. The second kind of thing that we're able to see is a persistent routing service that impersonates to marketing company. We will talk about that. It's a bit obscure, but it's a really important piece of the research, and we'll go through that in a couple of slides. The third thing that we're able to see is the filtering of non-browser traffic using an HTML anchoring. And let's try to explain that. What does that mean? So you remember the link that we saw before, and we have the hash bound and the token that goes afterwards. So as I mentioned, when I press on that link, the only value that will be sent to the server will be from this point to this point. The other value, the hash bound, will only be accessible using JavaScript on the browser, which means that adversary created a situation of which that if you will take that kind of link and try to run that link in a context of a non-browser functionality, meaning if you will take a JavaScript, if you will take a Python script and try to scan URLs using that given URL, since Python is not an HTML, it's not rendering the page as browser, right? It's not having a JavaScript engine. As a result of that, once you will execute this code, the meaning of that the functionality will not be executed, okay? Because this code is saying, hey, so take the URL that you saw before, do some splitting of that based on the hash bound, take the token that you were able to see that was only in the context of that URL, it was not sent to the network, which is a bit important, and take that token and reconstruct a URL, a new URL, that new URL you will be redirected to that URL. So your Python script will not be able to work on that kind of functionality, again, because our Python is usually not executing JavaScript, unless we implement something more specifically to do that. And that's where the redirected URL, the third step, and that will be created, right? So in that sense, what we see here, that's another kind of mechanism that's being used by adversary to say, hey, so we acknowledge there is a lot of vendors out there that scan URLs. Some of those vendors are not spending enough time or resources to run a full headless browser functionality that knows how to render pages and execute the code on those pages. And as a result of that, those vendors and those tools will not be able to follow the link that we were giving to the victims, and a result of that will not land on the landing page. And if they are not landing on the landing page, they cannot detect that it's a scam, right? Cool, so we talked about that. Step number 3, landing pages. And in that context, a lot of technology and a lot of techniques that were used, rotation of domain names. Meaning, well, it's the same website, and if I'm standing, for example, beyond a CDN vendor that gives me those kind of services that enable me to buy a domain and redeploy that domain to that website very easily without any problems, that will result in a situation of which, even if my domain was classified as malicious and was added to all those blacklists and list of URLs and domains that indicate that that domain is phishing, it's only a matter of me pressing a button, buying a new domain, and associating the website to a new domain. And obviously, that's a challenge from a defensive point of view. Other techniques being used, JavaScript obfuscation on the website, making it very hard to look into the content being delivered and try to understand what's the content being delivered without rendering it, which again, it's possible. It's not that it's not possible, but it takes a lot of resources and time to do that, and that's obviously challenging from a defensive point of view when you have to scan and do that for millions of domains and URLs every day. Dynamic content, some of the content being delivered in the website was dynamic, and randomly generated URLs. Again, when you are trying to blacklist URLs, and those URLs are randomly being generated, for each victim has its own URL being generated just for his usage, that creates challenge when you try to manage those list of URLs. You need to be smarter in order to do that, and that's obviously some challenge for us from a defensive point of view. So it's a whack-a-mole kind of situation, right? Because if I was doing that, I will try to take down those redirecting URL, those URL shorteners, for example, a new one will be introduced, and as a result of that, the scam will continue to execute. And if we will take down some of the landing pages, right, a new landing page will be introduced, and everything will work as expected. Now, how do I know that and how it works in practice? So in practice, the thing that I was able to see is that URLs that I had indications of those URLs being malicious 10 months prior to me using those URLs were still active. In other words, the initial URLs that was created to create a scam was not taking down. The website, the landing pages were taking down, which is what we usually do, right? We are mitigating those threats by taking down websites. And once that was done, the URLs remained the same because the network of that scam made it possible to change the landscape while the original redirecting URL is still valid. Okay? So what I'm trying to say with all of those techniques, and there's more of those techniques, the bottom line that I'm trying to say here, and the point being said, is that we are creating a lot of security products that know to fight back against a lot of threats out there. In the context of us, threat is phishing. An adversary understands that. And as a result of that, they were able to map between the core capabilities that we are doing to some evasive techniques that they are using to make sure that their scam will long live. Again, I said that before and I will say that again. It's not an issue about making sure that the scam will stay forever. The scams will be detected. It's very volumetric, very noisy kind of scams. It's being detected, it's being mitigated. But the issue is how much time it will take us to the point of time that we will mitigate that scam for a new variant or a new version of that scam to appear again. And all of those techniques create a situation where it takes us much more time. So let's take two examples, right? So there is a defensive capability known as security crawlers, right? You give a list of URL and they crawl the internet, whether those URLs are suspicious or whatever, and they will try to retrieve information of those URLs to be able to classify those URLs as being malicious or not based on the landing page, right? And when you are using the URL encoding functionality that we saw before, that the adversary are doing, in some cases, some of those crawlers will not work well. They will not be able to detect those given URLs because they will not go to the landing page. They will be blocked on the way. Another example would be defensive capabilities that known as URL blacklist and takedowns that are being done to phishing websites. Now, the usage of URLs that constantly change, right, and domains that are constantly changed, that create a lot of challenge. We are doing that. We're continuing to do that. But in a sense, adversaries understand that that's our actions, that's the way we operate, and they try to, in a sense, make it much harder for us to detect those kind of things or react to those things, right? And the motivation or the objective from an adversary point of view is, in that case, delay the takedown or the blocking, right? They will gain more time means more victim mean more efficiency of the scam. Now, there are some strategic gaps that I want to talk about, right? Defensive versus, defender versus adversary. So as defenders, we had a tendency to look into the problem in very distinct way. We are saying, hey, we are measured by detections and takedown, right? If you will go to security vendors that talk about phishing, it will usually tell you, hey, I have that URL in my list or not. I was doing takedown to that given website, and I was doing my job. But adversary had different kind of way to look into that. So they're measuring different things. They're measuring engagement time, engagement rate. How many of the visitors to the website actually ended up with giving their credentials? Time to detection. How much time it took us to detect that, right? If it takes us an hour versus 3 days, that makes a lot of difference. The difference is the number of victims that will fall into that scam. Number of visitors, right? If we have a lot of visitors or not. And campaign persistency. How much that infrastructure that we built, again, adversary point of view, how much of that infrastructure is still stable, working, and not being mitigated. And number of victims, right, that what we will see, will result with much more money. They're not saying that they, like, not that I know what they're saying, but their approach is not that they're trying to evade detection. Detection will be made. It's high-scale attacks. They are being detected. The question is, how much time? And we fall short by that, because we're not reacting well to the threat out there. Now, we'll go back to that, but before going back to that, right, I showed you some campaign, but I want to tell you that I was doing some more research into that. Because when I looked into this schema of very high-level schema of the network that was used, what you can see, there is a component that is really, really stable inside of this schema, which is the routing component. And I asked myself, well, what's for me to go through that and better understand what that routing component means, what that routing component do. So before doing that, So that routing component that I'm trying to focus on is the same routing component that was doing the HTML anchoring. And I don't know if you remember, but the URL for the anchoring was not the slash. It was slash something, I don't remember the link, okay? So I was going to the domain itself to see where that URL is located on. And when I was doing that, I was able to see the following website. Hosting that URL in a sense. And looking into that website, I said to myself, hey, so Aria is a top consulting company specialized in business growth using online marketing and conversion optimization tactics, when it's really keywords for marketing in many ways. I think so. And I thought to myself, so maybe behind the scene, we are seeing someone that abused some marketing company that do affiliation of advertisement and stuff like that, and pass the traffic through that kind of platform, and by that collecting information on the users, and in a sense abusing that system. So I checked it out, and there were some details on that website saying, hey, their phone number, some address in San Francisco, and I checked in Google Maps, and there was some indication on that, and I was saying, okay, so it looks to be legit, but I'm not sure what, checking that more thoroughly. So it's trying to collect a lot of information that will enable me to make the decision whether that given website is malicious or not. So I looked in the domain that was used, and the domain was registered in May 2021, okay? Which is not ages ago. Definitely in the context of me doing this research. First indication for malicious usage was March 2022, okay? I was looking into VirusTotal. VirusTotal will enable us to look into Intel and make decision based on that, and there's a lot of information there. It's shared information, a lot of vendors sharing their information is there. So that enables you to get some insight that are not trivial. And looking into that domain in the context of VirusTotal, and the signals for that domain being malicious were very weak. There was only one vendor saying that domain being malicious, okay? Which, by the way, it's not a good sign, right? If you look into VirusTotal, you are looking for numerous kind of indication to make sure something is malicious. If one vendor is saying that, it might be that it's malicious, but it's not a strong indication. Now, as we mentioned, we were focusing on the routing component, but there is, from the routing component, we're able to see that we are being redirected to a landing pages. And I was able to track 30 different landing pages that were redirected from that given domain. And looking into those domains in the context of VirusTotal showed me that 9.5 on average, 9.5 engine classified those domains as being malicious. So what we are seeing here is a routing component that we think it's malicious, we're not sure about it, that land victims into landing pages that are definitely malicious, which says in many words that it's probably malicious by essence. Now, more to that, I was trying to figure out, so how many visitors are going through that routing component? And in order to do that, I used SimilarWeb. SimilarWeb is a website and a company that creates statistics of internet. They are being used for marketing purposes. If you want to know where your visitor came from, what kind of browser they were using, where they redirected from and where they're heading to from a marketing point of view, marketing will take it, create some sort of an understanding of how visitors to website looks like and how to improve that and how to improve the SEO for the website and so forth. And since that website was highly popular, meaning with a lot of visitors, between 50 to 150K visitor per month, that means that that website got really good ranking according to the number of visitors that goes to that website, and it was published in SimilarWeb, so that enabled me to know that. And site ceased to exist in April 2023, meaning someone took it down, right? Which is the final indication that that website was not legit. And if we do some sort of an estimation for that and try to better understand the business behind the scene, because now we have some numbers, so we are seeing a website that was active for 13 months, at least 13 months, with over 1 million visitors, okay? So let's do some math about money and what adversary we're doing as a result of that. So let's say 1 million visitors, 0.1% of them are victims, which is a very conservative number, but realistic one. And we are adding up with 1,000 credit cards that were stolen. Credit card credential in the black market will be between $5 to $150. Let's go with the sort of a median, which is 50. And we're seeing 50K revenue for that kind of scam, okay? Which is impressive and not impressive. It's not that impressive number, but it's just the beginning. So I was going down into that marketing website, and I looked into that, right? That's the website on the right side. And on the left side, you can see that on that website, we were able to see that we have John, who is the general manager. And I was saying to myself, it looks a bit like a template. Where's for me to do some of my searching in Google's skills and more, and try to figure out if I can see the usage of the template out there. So apparently that John is also Patrick, who is CEO, who is also Pierre, who is co-founder, and he's also John, who is Chief Executive Officer. Okay, so that led me to believe that that website is not legit whatsoever, right? It's a template, it's not a company, it's not a real company, and that's changed the picture, because that led me to say, okay, so if I know it's a template, let's try to figure out how many usages of that template I can see out there, and to verify each usage of that template by looking for the anchoring functionality that we talked about, right? If I see that functionality being used on a given website out there that use that given template, that's a 100% indication that that given website is associated with that malicious activity that we were able to see so far. So I was doing that and was able to see nearly 11,000 domains being associated with the template, and I scanned those domains because some of them were active and some of them were not active. Some of them were just usage of the template without malicious intent. And I was able to find 1,900 different active redirecting functionality. So it's not one website, it's 1,900. Hosting services, so I asked myself, so how many hosting services are hosting that activity? And what I was able to see that over 20 different hosting services are doing that. And that's an interesting point, because what that means is that somebody created something in a high scale, highly distributed kind of scam. And again, when we talk about why it's being done from an adversary point of view, if you want to do a takedown, and that activity lies on the same hosting services, you only do one activity. You need to go to that hosting services and take it down. But if it's spread it on different infrastructure, that means you need to open kind of a negotiation with each one of those hosting services infrastructure and do those takedowns, which takes, by the way, a lot of time and a lot of effort. Therefore, you need to be highly motivated to do that, which is not trivial these days. Now, more to that, I was able to collect 25 different brands being abused in all those scams in association of those scams. So this is a kind of a scam that doesn't target one brand and one activity. It's a scam that uses some sort of a template of this question quiz kind of activity and goes all over the place and try to engage as much users as possible with all kind of brand being abused in campaigns that go periodically on different times of the year. And that's part of the scam and part of the scales of the scam. Again, VirusTotal, I was taking those 1,900 different domains, and the scores for all those domains were very, very low, meaning they are staying behind the radar. No one detected them. No one classified them as malicious. And therefore, they are long-living. And therefore, the infrastructure of the scam is continuing to be alive. Now, let's go back to adversary economy, right? We talked about 50K for that domain that we saw before. Now we have 1,900 domains, so numbers are a bit different, right? Yes and no, but basically yes. So what we are saying, it's not 50K, it's something else, it's different scale. And think about that as a motivation from an adversary point of view. They have the ability to create money out of nothing. Yes, they need to build some sort of an infrastructure. Yes, they need to maybe pay for some of the services that they are using, but they are getting money out of that, which is worthwhile in a sense, unfortunately. Now, that was the first template that I was able to see. I was doing some more correlation and was able to see that different templates are being associated with the previous template that we were able to see. And this time, the template that I was able to see is Passionate Web Company. So it's not just those 1,900 domains, it's more than that. In that template, we're able to see 28,000 domains associated to that. Scanning those domains, I was able to see over 9,000 domains that are active, hosting the redirection functionality. Different scale, different story, different money associated with that. But no, I wouldn't factor that. It's not as if you can take the 50K that we estimated from one of those routing domains into the number of domains that we are seeing. A lot of that infrastructure is redundant. A lot of that infrastructure is using adversary for a doomsday. They build it. They are not using all of that, but we need to be aware of that. And yes, there are more templates. Some of them are a bit smaller in numbers. But again, think about it from an adversary point of view. Someone is investing a lot of time, a lot of effort to build something that long-lived, that do the job, and makes our life much harder to detect those kinds of scams. So let's do a short recap. Okay. So we faced techniques, right? We saw countless amount of techniques being used, and again, the goal is to make our life harder from a defensive point of view. Getting more time, meaning more engagement, meaning more victims, meaning more money. Infrastructure, we're able to see, right? If we summarize all the things that we saw, over 50,000 associated domains, 15 out of them are active domain. Okay, someone bought 15,000 different domains. These are not compromised websites. These are domains that were purchased, being maintained. They are not on the same date. They are not the same owner associated to them. It's someone is working on that. That is their day job. And it's been run on over 20 different hosting providers, and we talked about the challenge of that before. So now we are talking about campaign that runs for years and not months. Right? With millions of potential victims, because we start to see the numbers and we can reflect that on the time that we see this campaign and the amount of domain that now we see in this campaign. And when we talk about the money, we're talking about 7-figure kind of operation. That's the estimation. That's what drives adversary. That's what makes that their day job. Okay, so at the beginning I was saying, hey, so it's a multi-layer story, and I was saying, hey, so it's a story about a really nice campaign, which is true, but not that interesting from my point of view. Very evasive, very ongoing, runs for years and not months, and targets millions and not hundreds of thousands of victims, okay? So that's one way to look into that, and it depends on how you look into threat landscape, and it's a legit way to look into that. The second way to look into that, as I mentioned before, is to try to better understand what stands behind the scene, what drives that. So I call it the factors and economies behind phishing scam. What drive adversary? What's the money trail for that? How they work, how they operate, and what makes their work worthwhile. But there's another way to look into that, and that's how we fall short, which is what interests me the most. Because at the end of the day, what interests me is to be able to build solution that will be able to fight back against those things. So I need to understand what we are doing right and understand what we are doing wrong, and that will enable me to go to my colleagues and friends and the people that I work with and for, and try to build solution that will enable us to fight back against that. So let's talk about why we fall short. First reason is because adversaries know how our defenses work. That they acknowledge that. They understand the limitation. They understand what we are doing where we are looking into email content and try to classify something as being phishing. They know how we classify URLs being malicious. They know how we scan those URLs over the internet. They know how we factorize all kind of things that make those URL maybe not as suspicious as one would think. For example, if a URL is associated with a website with a good reputation that might change the classification of that URL. We need to remember it's not about tracking 1 URL, 2 URL, or 100 URL, or not even 10,000 URL per day. From an industry point of view, we are dealing with millions of URLs being introduced daily, and therefore we had to build systems that will enable us to do that. We don't have a headcount that will do manual job, and therefore that's what adversaries are targeting. We know the threat landscape is overwhelming, as I just mentioned, and that's obviously a challenge. Trying to incriminate infrastructure is very hard. When you go to those hosting services and tell them, hey, I have a website, and this website is not hosting phishing website. It's not malicious by definition as that. It's just, it's doing a redirection to some malicious website. And they're saying, okay, so you should bring me more evidence for that because that's our business. There are some customers of us that pay us money and hosting some services on our property, and you're telling that those properties are associated with something malicious, they are redirecting to something malicious, right? There's a lot of evidences on VirusTotal on that. So you need to bring us some proof to make our decision much easier, and it's not trivial as you would imagine. The infrastructure that they are using running on many hosting services, so that process that I just mentioned need to be done on each one of those hosting services, making it very complex. We focus on landing pages and an industry. We always say, hey, so the landing page of the phishing scam or the malware associated with that or C2 is that domain, right? That's where everything exists. But what we see here, that from an adversary point of view, that doesn't matter. They know how to build an infrastructure that makes sure that even if we take down the landing page, scam is still working, and we talked about that. And our KPIs are a bit different, and I think that's the most important thing from my point of view. We need to be more aware of time. We need to act fast. We need to count victims. Again, we need to make priorities of what we are detecting as severe versus less severe, right? If we see a website that we think it's malicious and there's a lot of victims that go to that website, maybe that works for us to be a bit more proactive in that sense and act much faster in that sense. Because again, at the end of the day, it's not 0 or 1. It's not about adversary not being detected, and it's not about us being able to block it at 0 day. It's in between. It's if we will do our job faster, the meaning of that is that the scam will be less effective, and as a result of that, that will lower the motivation of adversary in a sense. So we are toward the end of the presentation, and as you can see, Natalie reemerged again and again, each time taking different brands, and these are snapshots that I was able to take. Different brands, text are very similar, different images. So Natalie is still here for a sequel or something like that, still being active, by the way. I think that's all for today from my side. Thank you very much.
Okay, we do have a few minutes for Q&A. Yeah.
Metrics are hard. How do you measure the victim?
So how do you measure victims and track that?
So if you have, in my case, working for a company that, Akamai, that has a lot of traffic, right? Traffic is not an issue for us. We see the traffic, and we can tell you very quickly and very easily if there is a lot of traffic going to a given domain or not. So that enables us to make priorities in that context.
How would a consumer, either of your services or not, capture some of that information? Do you guys publish that sort of intelligence?
So the question was whether we are capturing that information and sharing that with others. So in a sense, we are publishing some of the domains popularity that we see out there. But if I would be honest, we're not doing that in the context of malicious, but more in the most popular website being used out there. It's being used as part of our products. We are not externalizing that because it's a sensitive kind of information, obviously. You can share something that might lead to, so if you're sharing something about something that's malicious, it's probably okay, but if you're doing mistaken sharing of something that it's legit, it makes it a bit not okay. So yeah, we don't have public records for that, but we're using that, obviously. Yes?
You've shown how following the infrastructure is challenging and hard. Have you considered following the money? How many payment processors, for example,
So the question was showing how we are following the infrastructure, but how can we show that we follow the money and those kind of things behind the scene, right? And the answer for that, it's not trivial. And B, in many cases, as a security researcher, you are not sure you want to go that path because it's kind of information that makes it a bit harder to get, and then you are being asked how you got that information. I know that in some cases, reaching out some of those hosting services and asking them those kind of questions, not in the context of, hey, give me the credential, I'm not interested in that, but trying to see if there is a correlation between different activity on the same hosting services that are associated to the same paying credentials, and they were pushing back and not giving that information, obviously, because it's a sensitive information. So it's very hard to try to track those kind of things. It's very challenging. Again, yes, but that's correct. But that's, as I mentioned before, the challenge is not to coordinate that with some credit card company. The challenge is that the ability to incriminate those kind of things. Because when you go to those hosting services and tell them, hey, so you have a couple of domains, those domains are doing redirection, but those domains are not containing anything, and you're saying no because? Exactly. They're saying, send me a snapshot. And you are, hey, so listen, I want to explain something, and I need to explain that to them. And obviously that's challenging and a lot of cycles, and it's a challenging thing to do, from practice. Yes.
What about working with law enforcement or helping to identify these scammers? Is that feasible or impossible?
So the question was whether working with law enforcement will be visible and possible in those cases, and the answer for that is maybe. I was not going through that path. There's all kind of policies that I have to apply to. I can tell you that from my experiences that law enforcement are saying it's all about the bar. So what are the money being involved? And in some cases, they will not say it out loud or out there, but they will tell you, hey, we also have a capacity, and small frauds are things that they will be challenging to face with because the volume and the amount of those kind of frauds. So there is some bar that can be involved, and I'm not sure we're crossing that bar here. And again, it's very volumetric. Everybody we're seeing this attack, it's like, I would imagine that if I will do a survey, 50% of the people here will say that they were able at one point of time see that kind of scam. It works for years, and it's very loud and very noisy and exists out there. So it's still there. So that's a tricky part. Any other questions? Okay, I think we're done for today.
We didn't have anything online, so. Yeah. All right, thank you. We'll have a few-minute break and reconvene at 4. I will turn it over to Ophir.
Thank you very much. So thank you guys, and I know it's the last talk of the day, so again, thanks for coming. I'm Ophir, and today we're going to talk about detecting process injection using network data. So before I start, I'll introduce myself. So if you guys have been to the last talk here of Or's, he introduced himself pretty well, and I too work for Akamai. So Akamai is a big corporate that specializes in cybersecurity, and specifically in Akamai, I work for the Hunt team. So before that, I was a research team leader in the military. I did that for 6 years in a defensive unit, and for the last 2, I've been working for Akamai. So we in the Hunt team, we hunt for threats, and we're basically an additional service over the Akamai macro-segmentation platform, also known as the Akamai Guardicore platform. So if we're going to talk about process injection, let's talk about why process injection. Why does this thing even exist from the first place? So process injection is basically an attack technique that is stealthy, it's reliable, and it's been working well for threat actors over the years to hide their payload, either if it's from EDR solutions, antivirus solutions back in the day, or just from security analysts. So let's talk a little bit about the history of process injection. So right when Windows came out, with Windows NT, we were introduced to the create more thread DLL injection, and also to the AIT hooking. After that, in the mid-2000s, we were introduced to more injection techniques, one of them being the SSTT hooking. And after that, we're introduced to process hollowing, also known as RunPE, and APCQ, which were first used in the late 2000s. After that, DLL reflective injection came out, and also in 2016, we were introduced to atom bombing in Black Hat EU, and doppelganging came out, which is another injection technique, and right after that, in the Elastic group, we're introduced to process ghosting, which we all know from dating apps. So, we're defenders, right? We're security researchers. We don't care about abusing these injection techniques, so let's talk about detecting them. We'll start with this example of the create more thread injection technique. And here, when an attacker uses this technique, he basically loads a malicious DLL from disk using the create remote thread or the antivariant API call, and basically takes his DLL and loads it to a specific process that he has permissions to. So what we can do is iterate over the legitimate process and look for an illegitimate DLL. Another one is the AIT hooking, which in this one, in order to make it happen, an attacker takes a legit process which imports legitimate DLLs and changes the addresses of DLLs of these functions to point to illegitimate code. So again, if we go over the process and the imports of that process, we need to make sure those addresses point to the correct locations. And the third one we're going to talk about is process hollowing, also known as RunPE, like we said, where here the attacker brings up a legitimate process, a real legitimate one, but swaps the code inside with illegitimate code. So he brings up a legitimate process. It could be from System32 or any other place that he wants to, and swaps the insides of it with his own process. And in order to detect it, we basically look for discrepancies between the so-called legitimate process, which is the outside of the process, and the code that the attacker inserted, which is the illegitimate code, which resides inside. Two of these are detectable using Sysmon. So if you have Sysmon deployed in your network, you'll find it is event ID 8 for create more thread and 25 for the process hollowing. So basically, if we want to take a broader look at the detection of them, we can see that there are main things that are similar in each of these detection methods. So there are two things we need. Either the ability to trace API calls or direct access to our memory. If it's kernel memory or user mode memory, but basically we need one of these two things, preferably both. So this is something we rely on when we detect these injection techniques. And the second drawback is that EDR bypasses are everywhere. When an attacker takes control of a host, if it compromises a server or an endpoint, the first thing you will check is what antivirus solution it has installed on it, right? If it's this EDR or that EDR. And the second thing you will need is to understand how he bypasses it. So we, as threat hunters, cannot always rely on the fact that the EDR will detect that injection technique. And think of it. Sometimes, as a threat hunters, we will have hundreds of customers, and each customer will have another kind of a security solution. So you cannot take for granted that the solution will stop the injection, or you cannot even take for granted that your customer will even have an EDR or a security solution. And the most important thing about our detection is that network packets don't lie. So what do I mean by that? Many host-based artifacts can be bypassed or changed or manipulated, but if you're an attacker and you're making communication, you will certainly have to take into consideration that the network might be monitored, and the network is much harder to mess with. So what would an attacker do? Let's say I'm an attacker and I successfully injected payload into a process. Okay, cool. So what can I do with it? So maybe I can communicate to a CNC server. I can send home a message. I successfully compromised this asset or that server. Maybe I want to deploy reverse shell to maintain persistency. Maybe I will start crypto mining because it will help my wallet get bigger. Or maybe I want to scan the network for to see what other hosts exist in it. Maybe I want to continue my lateral movement attempts. Or I can do whatever I need. So again, this is all dependent on what the attacker wishes to do. So how can we, security researchers, analysts, threat hunters, detect all of this malicious or possibly malicious activity? So let's talk about detection. But before that, let's talk a little bit about my job. So in Akamai, the good thing is we have a lot of data. Lots and lots of data from hundreds of customers around the world, but not only basic 5-tuple data or firewall logs or anything like that. We have process-level deep data, meaning we can know for each communication which process initiated that communication and also which process received the communication. So we basically have all the fields we need to know about each communication session. So what we can do with it? Think that we have month and month of this communication data from so many networks. We can basically learn how each process behaves, and then when the process behaves differently or in an anomalous way, we can catch it doing anomalous things and start investigating. So how does a process communicate? Well, that's a hard question, because each process communicates differently, and the interesting is that even though we might see the same identical processes in different networks, those same processes might be still communicating differently when they're deployed in different networks. So I know it's a little bit small, so let's zoom in on an example here. We can see that, let's take the second line. So in the Postgres process, even though you say, okay, it's a Postgres process, so how many ports should it be using? 2, 5, 15? So from our data, we can see that it generally uses more than 1,000 different destination ports for outgoing communication. Same for the other two. So they use many ports while communicating in the network. So how can we use this data that, as you understand, that varies a lot to catch those processes when they communicate in an anomalous way? So in our research, we saw that even though some processes might be using many destination ports, if we classify them to something we call port groups, we can know that even though they're using many ports, they're generally using the same kind of applications that are tied to those ports. So to understand it better, we can look at some examples. The Docker proxy process uses 61 different destination ports, which is not a small number. But if we look at what kinds of ports it uses, we can see that it generally uses high ports, so those long list of ports, and the RPC port of 135. And that's it. So it might be using many ports, but not so many applications. So by using these port groups, so-called, we can give better context to the detection algorithm and better understand how each process communicates. So we took the whole port range and classified each port into some port group. As you can see, I gave here some examples. So the DHCP translates to these 4. If we see a process using one of these 4 ports, we can say, it's using DHCP. And the full port classifications is present on the Akamai blog. You can surely enter it later. And while developing this method, we had many, many questions rise up. So the first one being, okay, I already bragged about how much data Akamai has, but how much data is enough to assume a process communication? Do we need a gigabyte of data? Do we need 100 sessions? And we can say, okay, we know how this process behaves. Maybe we need amount of data from more than one network. Maybe we need data from 100, 10, 2, I don't know. Another question is, okay, so processes do not always behave the same. So if we see a process behaving in a certain way in one network, does that mean it will behave the same in all others? Maybe it's an anomaly that should be checked. Maybe we should take it for granted. Okay, so it behaved like that, and we should take it and insert it into our baseline. Also, should all anomalies be treated the same? So what do I mean by that? Let's say we have a process that communicates in SSH. We've seen it in 100 networks, and every time it uses the SSH protocol. One time, out of the blue, in a new customer, it suddenly used port 50,000. So let's say a high port. Is it interesting? Maybe. Is it an anomaly? Yes. But is it interesting? Is it more interesting if we saw the same process suddenly use RDP? So both are kind of the same anomaly, but here it's using different ports. And the most important thing is, can we hunt for anomalies in every process? Maybe some processes are more stable than others. Maybe some are random. Maybe there are processes that it doesn't matter what it will do. It will be very hard for us to find it doing anomalous communications. So in order to answer that last question, we took the processes that we have data about and classified them into specific groups. So we try to measure if a process is consistent and it's easy to detect anomalies in, or maybe it's inconsistent and it's random and it will be very hard seeing when it does something malicious. So the first group would be the stable group. So that's pretty straightforward. It means the process behaves the same in all of the networks we're monitoring. And the unstable group means the exact opposite. So for every network we're monitoring, it behaves completely differently, which will be random and harder to look for anomalies. So if we'd stay with these two groups, we will not be achieving too much, because not all processes obviously go into one or the other. There's still more stuff to be filled in the middle. So we came up with this third group, which is the semi-stable group. This means that the process behaves the same, but only in the range of ports that is the non-high ports range, meaning from 1 to 49,000, the process behaves the same. So for each of the processes in this group, we completely ignore the ports in the high ports range and just focus on these ones. And applying the same logic, we came up with these three groups that are based on the Nmap top ports parameter. So Nmap maintains a list of the most common ports that is known in the wild. Meaning if you're a pen tester and you want to scan a specific host, but you don't want to be too noisy, you can just use the top ports parameter and specify how many ports you want to use. So if you want to scan the 50 most popular ports, just specify 50. So we use this classification by Nmap to basically classify each port, just like in the semi-stable group, by that specific group of ports. So let's take an example. If we see a process communicate randomly, but inside the Nmap top 12 group, it will communicate the same in all networks, we can say, okay, this process is Nmap top 12 stable. Okay, so let's say we classified all of the ports into these classifications, and now all processes I meant. So each process has its own category. So is this methodology any good? Well, it has its cons and pros. So we'll start with the pros. First, I don't know if you saw that, but that last line means that we're monitoring only processes that we saw in 3 or more customer networks. So like I said, we have hundreds of customers, and for each of the processes, we will take it only if we've seen it in 3 or more, which means it's a popular process, and it will surely make us have enough data about it. So with that number of networks means we have enough data about the process. We have sufficient data, meaning we have at least, enough of the amount of data, and also we have variation. Because each process, like we said, behave a bit differently in each network, we have a good variation because we saw it in at least 3. And it also helps us because let's say we have an incident about a specific process. Now we have 3 customer networks that we can compare it to. So it also aids investigation. And the second thing is that the number of communication sessions won't affect the judgment of the detection algorithm. So that's a weird sentence, but what it means is that if we saw a specific process, let's say one process is deployed in a customer and suddenly that customer has a spike, and we see that this process receives lots of communication, but it still uses the same port. So why would we take into account the number of sessions that it initiates? So we don't want to do that, and by looking at a process per customer, it helps us avoid noise. And of course, this method has cons as well. So unfortunately, most processes do not appear in at least 3 customers. Most of them could appear in 1 or 2, and with this, we will be missing them, as they will not go into our learning algorithm and into the baseline. So, we could have hundreds of customers, but still, if, let's say, a specific application is only installed in 1 or 2, even if it's deployed all over the customer network, we will still not monitor them, which is sad. And the second thing is, we talked about the use of port groups. So let's say we know now that the process uses these 2 port groups. Which one does it use more? Maybe it uses this more often than this. Maybe it used this port group once, and it will be interesting for us if it used it again. So we're not keeping this information, we're not tracking it. And this is the second con of this methodology. So with this, we moved on to a new way to study these processes. And we used the support and confidence measurements taken from the world of data mining. Support, meaning the amount of data we have about the process. Do we see it often? Do we see it sometimes? How many times have we seen it? And the second thing is the confidence, which measures the relationship between 2 items in the data. So if a process uses a specific port group, does it use it often or less often? We will see an example soon. So let's take a look at some simple example. So for support, let's say we're a shop, we're a grocery store, and we have a data set of transactions. So out of the 1,000 transactions we have, 300 of them are of apples. So the support of apples in our data is going to be obviously 300 divided by 1,000, which is 0.3. And regarding confidence, so if out of these exactly the same 300 apples, half of them are red, then the confidence of apples towards red apples is going to be 1/2. So 150 divided by 300, so 50%. Okay, So how does it look like in our data? We're researchers. We don't care about apples and, we care about these processes. So I gave an example here. We can see that the SQL.exe process has the support of 0.003, doesn't matter, and it uses 3 port groups. So SQL, high port, and other. And the confidence of each one is written there. So it's easy to see that this process uses SQL more often than the others. And another thing to note, that if before we were looking only at how a process behaves in a customer, now we have another kind of measurement. So our data point would be of hosts, a process, and the port group. So what does that mean? That instead of only looking at a network, we would look at the number of hosts in the network. Because before, remember when I said, let's say we have a customer with a process deployed all over it, it's a lot of data and we will lose it. So here we take into consideration the number of hosts that we've seen the process run on. Okay, so how will the detection logic look like? We learned how a process behaves. We can compare it to new data. And we're going to use a sliding window baseline in order to achieve that. So, as you can see here, what's happening is that we take all of our new data and we compare it to the history of the process. In this example, we take the data of today, so all of the communication, all of the process communication that's happening today, and we compare it to our baseline, which consists of, in this example, it's a month of data. It could be more, it could be less, depends on your data retention. And after we compare the new data to the old data and alert about the anomalies, the date shifts, and the data of today will be used for the baseline of tomorrow. So tomorrow's communication is going to be compared for today and the rest of the history. So let's take a look at some code, because our detection doesn't look like this. It looks more like real code. And we will take a look at this sample SQL code in order to explain it better. So, as you can see, in this subquery, we take all the connections that have happened today. So these are the new connections. And you can see that we take each destination port, and like we did before, we classified it into a specific port group. Okay, so we have the communication of today. And now we select the baseline. So we select each process, the relevant support, which port groups we've seen it use, and then we have the confidence for the relevant port group as well. And you can see some interesting condition here at the bottom, that we take only processes with specific support. So here the support comes into play, meaning we only want to take processes that we have enough data about. So how does that affect our logic and our detection? So higher support means we will have less processes in the baseline, but we will have more data about these processes, which will generate more reliable incidents. The incidents will be more based, as each incident will be based on, more data. Though it has the drawback of less processes in the baseline, so we might be missing some of the processes if we used a lower support threshold. And after that, we're going to compare the new communication that we receive to the old communication. So here you can see that we select our baseline and we join the communications, the new communications of today on process. So we use a join here and not a left join. So basically, if we have a new process that does not appear in the baseline, then we have nothing to do with it, right? So we only want to compare processes that we know how they communicate. And then you can see in the condition that we want to select all port groups that have not been seen before. Okay, so we have that. But if you remember, we asked a question before about what if we've seen a process communicate in some sort of way, and we still want to see it again when it happens. Because I gave the examples that out of 100 networks, we see it in one, but it could have been initiating only one session, and it is still anomalous, and if it happens again, we will want to know. So here the confidence comes into play. So these are just sample numbers, but what that means is that either it's a new port group that have never been seen before, or we've seen that port group before, but we've seen it so little that it's still interesting for us if it pops again. So this is the second condition. Okay, so like all detection algorithms, we have our false positives. And before we talk about how we deal with these false positives, let's talk about what kinds of false positives we might have. So from our experience, there are a couple of false positives that could occur with this detection method. So there could be proxy servers deployed in the customer network, which will make some processes communicate in another way. Also, think of an IT admin that suddenly switches the software from working with IP addresses to host names. Okay, for him it's nothing. The software still works, he's happy, he goes home. But what does that mean for us? It means the process suddenly communicated in the DNS protocol. It suddenly started sending out DNS requests, which if we haven't seen that before, it might appear as an anomaly. Also, domain authentication could cause various packets of different protocols to get generated. Sometimes the software manufacturer will release a new version that communicates just a little differently, or maybe it has a network-wide configuration, and we will see an example of one of these false positives that corresponds to that type. So here, we have an example of some process that we've only seen it communicate in these two ports. So you can see port 80 and port 443. And suddenly, one day, it started communicating using port 1111. Have any of you seen that port before? So it's a weird port. And if we look at the history of how this process communicates, we can see that generally speaking, it uses 443, 80, and contacts various kinds of destination domains. You can also see how many times it contacts each. And down below, you can see the anomaly that we have three logs of the process using the specific port to a specific IP address, so we don't even have the destination domain. So we kept looking, and we had a conversation with the customer, and like I said, this is a false positive. So at the end, what we found is that that specific port was just a port that was configured so processes could communicate to the internet gateway in that specific network. So yeah, sometimes you'll investigate some anomaly and it will be a false positive, but it's still interesting to see them and learn from the so-called mistakes and then fix your detection. Okay, so what can we do about these false positives? So there are two things that we can do. The first one is check if this behavior is used in that specific network. So if we've seen other processes using the same port, and we've seen other hosts, so not just one PC, we've seen other hosts communicate the same way, and we've also seen the same kind of communication happen for a long time, we can know, okay, maybe it's an anomaly, but we've seen this happen before, so it's probably not worth wasting our time on. Maybe we should investigate more interesting incidents. And the second thing is that we can learn from past incidents and maintain a specific allow list for either specific processes or specific customers or networks, and generally try not to face the same incident twice as long as it's a false positive. Okay, so all of this would be for nothing if it wouldn't detect any real attack, right? Because we're not just writing detections to have fun. We need to detect the bad guys. So I'm going to present you how this method detected an actual injection. So it started out with us onboarding a new hunt customer and running this detection method. And what we found is 5 processes which deviated out of the respective baseline. So as you can see, you might even recognize some of these processes because they're running on basically any Windows machine. And they started communicating to large parts of the network using the SMB protocol. And they were all legitimate processes with injected payload. And you can see a screenshot from VirusTotal. And this corresponds to one of these processes. And it's truly legit. And the image from disk is clean. And the interesting is that you will not find them in the history and in the baseline using SMB. So they're all using other protocols, but they never, ever used SMB before. So we have an anomaly here. And how does it really look like? So this is a screenshot from the Akamai microsegmentation platform. As you can see, we found this behavior on 3 total hosts. On one of them, it looked like this. So a specific host suddenly communicating on SMB to other parts of the network. And on the right-hand side, you can see one of these processes communicating from the system user to other hosts on SMB. Okay, so after we had this incident, we started investigating. We looked at scheduled tasks and services and files and commands run and communication. And we looked for communication that was not seen before and found these 2. So on the bottom, you can see this svchost executable running from this weird directory, communicating to some IP on SMB. And the second thing is that you can see HTTPS communication to some unknown domain. And so it's running from system32, and the process is named DLL host X, which might trigger something in your mind, but processes are generally not named this. This actually masquerades the DLL host.exe that actually really exists in system32. So this is just to evade detection by some security analyst and to look legitimate. So we find these on 2 hosts, and we kept looking. And as you can see, these 2 executables are known to the cyber community and flagged as malicious on VirusTotal. So the DLL host X is a crypto miner, and the svchost is an Eternal Blue scanner. Okay, Eternal Blue 445, interesting. So after we kept investigating, we found the calling script. So let's go over the script quickly. And we can see that it first writes some string into some exe file and copies itself to another directory. And I'm going to speak like this script is actually running these commands, but what it's really doing is just preparing some bat file that it will run later. So after that, it echoes some asterisks to eb.txt. And we found that this actually, what is eb.txt? So this is a reference to the Eternal Blue vulnerability. So the script here basically marks which vulnerability was used to affect and infect that host. And after that, it decides to tunnel DNS communication to Cloudflare public DNS server, and it receives communication on these 3 high ports using Netch, and communicates those requests to 1111. After that, it makes sure that a PowerShell scripting language exists and runs some more, runs a PowerShell command to fetch some malicious PowerShell code. And so this is the actually decoded, this is base64, so this is the decoded payload. We can see that it contacts some CNC servers and runs additional payload that it downloads. And what does this payload do? It does 3 things. So it collects information about the host, host name, IP addresses, MAC addresses, things like this, and sends them to the attacker. It also downloads a Monero crypto miner and runs it via a scheduled task, so it's persistent even if the host decides to restart. After that, it does a couple of more things, so it makes sure that the task scheduler service is running, and then it deploys some scheduled tasks. It uses the same name for the scheduled task with different executables. It creates, it deletes, it runs. Here, as you can see, it downloads using the MSHTA executable. It downloads some additional JavaScript payload to run on the host, and then runs some other scheduled tasks. And at the end, it looks, it also starts a service that was installed beforehand, remotely. And the last thing it does there is just make sure that no more than 10 CMDs are running. This is probably just to make sure that it is not stuck in a loop of deployment. It then deletes the username, the administrative username that the attacker created. You see the payload is running. There's no need for a backdoor user. And at the end, it runs the script, runs another executable, and deletes itself. So if you followed along, at the end, we have one of these scheduled tasks still deployed, and we also have the scheduled task deployed from the PowerShell encoded command. OK, so as you can see, these domains are malicious. And they're registered. This is just some of them, but they're registered to the same organization. And you can see in that script there are a lot of IOCs that we can leverage in order to detect more affected hosts and find all of the places the attacker reached. So as you can see, just by communication, on the right you can see a couple of hosts listening on this exact port the attacker specified. So here we can find more affected hosts, and on the left-hand side we can see communication to Cloudflare's DNS service. So using these communication methods that the attacker used, we can find the rest of the infection. And just before I touch on the next things that we did, I'll just talk about OSQuery for a second. So if your guys are not familiar with OSQuery, OSQuery is an open source agent that is developed by Facebook. It has been developed for a couple of years now, and what it does is let you ask questions about your hosts. So it has an SQL-like, you can ask questions like in SQL form, and you can query many, many tables regarding scheduled tasks, services, files, hashes, and many other things. And fortunately for us, we have it already integrated into the microsegmentation platform. So using OSQuery and OSQuery capabilities, we could take these IOCs and look for them in the network. So as you can see, you might recognize some of these files from before. We're looking for the malicious files the attacker deployed. We're looking for the username that it used. We already know that it uses the Eternal Blue vulnerability, which is crazy how it's still working. But it used the Eternal Blue vulnerability to deploy itself on other hosts in the same network. So we want to know if there are more hosts that maybe have not been affected but are vulnerable to Eternal Blue. And we also looked for scheduled tasks, also the malicious service that it used, and more. So even though the attacker used randomly generated names, generally speaking, the behavior could be compared to other attacks that it did, and we can contribute all of the activity to the WannaMine attack group, also known as BP. So this attack group is a crypto mining group, and this threat actor has been active since 2018 and still active to this day. So even though he hasn't changed his tactics too much and using a vulnerability that was once supposed to be at least patched in 2017, it's still working for it, and it has been active for what? It's like 6 years already. OK, so we talked about detecting anomalies in outgoing communication. we have the process data, we know how it communicates, we can find when it communicates in an anomalous way, but you guys might be asking, okay, so if we have that data already, what about incoming communication? Because we know what processes are listening on what ports. So, from our research, we found a couple of things. First, most malicious communication is outgoing communication. The attacker compromises a specific server or endpoint, and it will generally want to either report back to base or keep moving, or generally speaking, just generate outgoing communication. And also, listening ports are easily configurable, meaning that how a process behaves, what ports it listens on, generally an IT guy who wants to deploy some software, the software will let him choose the ports that the application uses, otherwise it might break. So this really makes our anomaly detection harder when we go and look at listening ports, which means incoming communication. But even though I just tried to convince you it might work differently, I can still say that it works, and it reveals interesting communication about the network in general. So if a specific application is deployed, and it's deployed using a specific port that was never seen before, it's still interesting for the network admins to know, oh, maybe we have a new path of communication that we didn't know about. So even though it might not be malicious, it could still be risky for the network security in general. Okay, so what are we going to do next? So first, we're going to release the actual communication baseline that we have. So it will be out in the upcoming days, and it will contain all the information that I talked about, so the process, the support, the confidence of the specific port groups, and the destination ports that we know how each process communicates. And I can say that this logic, and this is the second point, the logic can be implemented using other data sets. So just like a process is tied to a port or a port group, we have other kinds of data that we can say the same about. So like a service that is tied to an executable. And I can say that we already implemented this kind of logic for services as well, meaning we want to find known services that are suddenly running malicious executables. So executables that are running from other directory or another executable name or anything like that. And another thing we can do is add more features to the detection. So we could work with other fields like destination domain or ASN, or maybe some processes only communicate internally. And then when they communicate on the same port but externally to internet, we can know that it's not supposed to happen. And yeah, I encourage you to try it. Try it using your own network data. So like I said, we're going to release the data set, but if you prefer to use your own network data to build a baseline, you can do that. It might be even more relevant as the data will be based only on your network. Maybe you can combine both. It could be really interesting. Many EDRs or firewall logs can contain process data. And also you can use, this is a screenshot from Sysmon, so you can use Sysmon Event ID 3, which has all that information that you need to do some similar detection. Okay, so any questions? Okay, thank you for listening.
All right, this is it for the day, folks. There is happy hour in 15 minutes down there.